Right now, as you listen to these words, the space between galaxy clusters is growing, not slowly, not gently. It is stretching at a rate that defies ordinary understanding. The voids between the great cosmic structures are expanding faster than light itself, and nothing, not a single force in the known universe, can stop it. Nothing we have discovered, nothing we have theorized, nothing we have even imagined is capable of halting this silent, relentless pull. The gaps between galaxy clusters are the largest coherent features in all of existence, and they are winning. Consider this. The nearest major galaxy cluster to our own is the Virgo cluster, and it sits roughly 65 million light-years from Earth. That is 65 million years of travel at the speed of light, the fastest speed any object or signal can achieve in the known universe. To put that distance into perspective, 65 million years ago, the dinosaurs still walked the Earth. The asteroid that ended their reign had not yet fallen from the sky. The entire subsequent history of mammals rising to dominance, the evolution of primates and early humans, the development of language, the invention of agriculture, the birth of civilizations, the construction of cities, the discovery of science, everything we know as human history, all of that happened in the time it takes a single photon of light to cross the distance from the Virgo cluster to your eyes. And the Virgo cluster is the close one. It is our neighbor. Beyond the Virgo cluster, the distances escalate into madness. The Coma cluster sits roughly 320 million light-years away. The Perseus cluster, about 240 million. The Shapley supercluster, one of the most massive concentrations of matter in the observable universe, lies approximately 650 million light-years from Earth. Between each of these structures, there is almost nothing. Not almost nothing in the way a desert is almost nothing, with sand and rock and the occasional creature, almost nothing in the absolute sense. Regions of space, hundreds of millions of light-years across, containing fewer galaxies than you could count on your fingers. Vast, silent, lightless expanses where a traveler could journey for millions of years without encountering a single star, a single planet, a single atom of anything. These are the cosmic voids, and they are growing. Every second of every day, the expansion of space stretches these voids a little wider. The expansion is not steady. It is accelerating. A mysterious force called dark energy permeates every cubic centimeter of the cosmos, pushing space apart from within, and the more space there is, the more dark energy there is, and the faster the expansion goes. It is a feedback loop with no off switch and no known limit. The voids between galaxy clusters are getting bigger, and they are getting bigger faster. The implications of this fact are among the most disturbing revelations in all of modern science. They do not simply concern the arrangement of distant objects scattered across the heavens. They concern the future of the universe itself, the ultimate fate of all matter, all energy, all structure, and all information. They concern whether the cosmos will remain knowable, whether future civilizations will be able to determine what the universe truly looks like, or whether the expansion will gradually erase the evidence of its own history, leaving observers stranded in a shrinking bubble of visible light, unable to determine what lies beyond the growing wall of darkness that surrounds them. By the end of tonight, you're going to understand why these distances matter, what they reveal about the structure and fate of everything that exists, and why the emptiness between galaxy clusters may be the single most important feature of the cosmos. You are going to see how these vast silent gulfs of nothing carry within them a message about where the universe came from, where it is going, where and what will happen when the last connections between cosmic structures are finally severed. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. The universe is not what it seems when you look up at the night sky. The stars and galaxies that fill our photographs and telescopes represent less than 5% of what the cosmos actually contains. The remaining 95% is darkness. 27% is dark matter, an invisible substance that exerts gravity but emits no light and cannot be detected by any telescope. 68% is dark energy, the mysterious force driving the accelerating expansion. And between the galaxy clusters, in the enormous chasms that separate one island of matter from another, that darkness reigns supreme. The dominant feature of the universe is not its light, it is its emptiness, and that emptiness is growing. Tonight, we cross those chasms. We measure the silence between the clusters. We trace the history of how these voids were born, how they grew, how they swallowed the matter that once filled them, and how they will eventually swallow everything the universe has ever built. We ask what it means that the cosmos is mostly empty, that the structures we admire are thin, fragile threads in an ocean of expanding nothing. And we confront a question that the distances between galaxy clusters force us to ask: what happens when the expansion wins completely? What happens when the voids have stretched so wide that no light, no signal, no information of any kind can cross from one cluster to another? What kind of universe is left when every island of matter is utterly alone? The answers are waiting. They are written in the silence between the galaxy clusters. They are encoded in the redshift of distant light. They are hiding in the mathematics of an accelerating cosmos. Now, let's begin. To understand the terrifying distance between galaxy clusters, we first need to understand what a galaxy cluster actually is. The word cluster sounds modest, almost domestic. It evokes a handful of things gathered together, a cluster of berries, a cluster of houses on a hillside. But a galaxy cluster is not modest. It is one of the largest gravitationally bound structures in the entire universe. A single galaxy cluster can contain hundreds or even thousands of individual galaxies, all locked together by gravity into a massive, slowly churning collection of stars, gas, dark matter, and radiation. A galaxy cluster is not a neighborhood, it is a continent, an entire cosmic continent floating in an ocean of void. Let us start with what we know well and work outward. Our own galaxy, the Milky Way, is a barred spiral galaxy containing roughly 400 billion stars. These stars are spread across a disk approximately 100,000 light-years in diameter and about 1,000 light-years thick. The disk is surrounded by a halo of old stars, globular clusters, and dark matter that extends much farther, perhaps 300,000 light-years or more in every direction. At the center of the Milky Way sits a supermassive black hole called Sagittarius A star, with a mass of roughly 4 million suns, 100,000 light-years. That is the diameter of our galaxy. A beam of light would need 100,000 years to cross it. If you could somehow board a jet aircraft and fly across the galaxy at 1,000 kilometers per hour, the journey would take roughly 100 billion years. That is about 7 times the current age of the entire universe, just across one galaxy, our galaxy. But the Milky Way is not alone. It belongs to a small family of galaxies called the Local Group. The Local Group contains about 80 known galaxies, spread across a region roughly 10 million light-years in diameter. The two dominant members are the Milky Way and the Andromeda galaxy, which is even larger than our own, containing approximately 1 trillion stars and sitting about 2.5 million light-years away. The third largest member is the Triangulum galaxy, a smaller spiral galaxy about 3 million light-years from Earth. The rest are dwarf galaxies, small collections of a few billion stars or fewer, orbiting the larger members like moons orbiting planets. 10 million light-years. That is the diameter of our local cosmic neighborhood. Everything we consider nearby, every galaxy we could conceivably visit in the unimaginably distant future, fits within this sphere. Remember this number, because it is about to seem very small. The Local Group is not a galaxy cluster. It is a galaxy group, and the distinction matters. A galaxy group typically contains fewer than 50 large galaxies and has a total mass of less than about 100 trillion solar masses. A galaxy cluster, by contrast, contains hundreds to thousands of galaxies, with total masses measured in the quadrillions of solar masses, which is 1,000 trillion or more. The difference between a group and a cluster is like the difference between a village and a sprawling city. The nearest true galaxy cluster is the Virgo cluster. It lies approximately 65 million light-years from Earth, roughly 6.5 times the diameter of our entire local group. The Virgo cluster contains somewhere between 1,300 and 2,000 galaxies. At its heart sits several giant elliptical galaxies, the most prominent being Messier 87. This galaxy alone contains several trillion stars, and at its center lies a supermassive black hole with a mass of approximately 6.5 billion suns. That black hole was the subject of a groundbreaking image released in April of 2019 by the Event Horizon Telescope collaboration, the first direct image of a black hole's shadow ever captured. The total mass of the Virgo cluster is estimated at roughly 1.2 quadrillion solar masses, spread across a region about 15 million light-years in diameter. Let those figures settle. The Virgo cluster is a structure 15 million light-years across, containing thousands of galaxies, each with billions or hundreds of billions of stars, each star potentially hosting planets. The whole thing wrapped in an enormous halo of dark matter that far outweighs all the visible matter within it, and this is the nearest major cluster to us. Light from the Virgo cluster takes 65 million years to reach your eyes. Every photon arriving from that cluster tonight began its journey when the dinosaurs were still alive, when the asteroid that ended the Cretaceous period had not yet fallen, when the mammals that would eventually produce us were small, frightened creatures hiding in the shadows of giants. But the Virgo cluster is not the largest cluster. It is not even close. The Coma cluster, discovered and studied extensively by the astronomer Fritz Zwicky in the 1930s, lies roughly 320 million light-years from Earth. It contains over 1,000 large galaxies, including 2 enormous elliptical galaxies near its center, NGC 4889 and NGC 4874. The total mass of the Coma cluster is estimated at about 7 quadrillion solar masses, several times the mass of the Virgo cluster. The Perseus cluster sits about 240 million light-years away. It is the brightest galaxy cluster in the X-ray sky, because the gas between its galaxies is heated to temperatures exceeding 50 million degrees Celsius, glowing intensely in X-ray wavelengths. Near its center lies the galaxy NGC 1275, also known as Perseus A, which hosts a supermassive black hole that is blowing enormous bubbles of relativistic plasma into the surrounding gas. In 2003, astronomers using the Chandra X-ray Observatory discovered that these bubbles generate sound waves in the intracluster gas, pressure waves rippling outward at a frequency corresponding to a B-flat, 57 octaves below middle C, a note so deep that a single oscillation takes roughly 10 million years to complete. The universe is humming in the Perseus cluster, but at a frequency far below anything a human ear could ever perceive. And these individual clusters are just nodes in an even larger structure. Clusters group together into superclusters, and superclusters connect through filaments to form the cosmic web, the largest scale structure in the observable universe. Our own supercluster, the Laniakea supercluster, was mapped by a team led by astronomer Brent Tully of the University of Hawaii, published in 2014 in the journal Nature. Laniakea spans roughly 520 million light-years and contains an estimated 100,000 large galaxies organized into several major cluster concentrations. Its name comes from the Hawaiian words Lani, meaning heaven, and Akea, meaning immeasurable or immense. Laniakea is not gravitationally bound. Unlike a galaxy cluster, which is held together by gravity, a supercluster is a transitional structure. Its boundaries are defined by the flow patterns of galaxies through space. Galaxies within Laniakea are flowing inward, drawn toward a massive gravitational concentration called the Great Attractor. Galaxies outside Laniakea are flowing in other directions, toward other attractors. The Great Attractor itself sits roughly 250 million light-years from Earth, in the direction of the constellations Centaurus and Norma, and its nature remained mysterious for decades because it lies behind the dense star fields and dust clouds of the Milky Way's disk, in a region astronomers call the zone of avoidance. Now let us attempt some scaled comparisons, because the raw numbers are becoming dangerously abstract. If we shrink the entire Milky Way galaxy down to the size of a dinner plate, roughly 25 centimeters across, the Andromeda galaxy would be another dinner plate sitting about 60 centimeters away. Two plates on a kitchen table, close enough to reach from one to the other without standing up. At that same scale, the Virgo cluster would be a collection of over 1,000 dinner plates scattered across a region roughly 16 kilometers from your kitchen table. Imagine standing in your kitchen and knowing that the nearest comparable collection of plates is 16 kilometers away, across empty countryside, empty fields, empty roads, and between your single plate and those distant plates, there is almost nothing. A few scattered plates here and there, your local group companions, but nothing like the concentration you see at the far end. The Coma cluster, at this scale, would be about 80 kilometers away. The Perseus cluster, roughly 60. The Shapley supercluster, one of the densest concentrations of galaxies known, would be more than 150 kilometers from your kitchen. The observable universe, at this scale, would span roughly 240,000 kilometers, nearly two-thirds of the distance from the Earth to the Moon, and most of that distance would be empty space. Let us try another comparison. Imagine you could drive a car at highway speed, 100 kilometers per hour, without stopping, without fatigue, without aging, forever. At that speed, how long would it take to reach various cosmic landmarks? The nearest star beyond the Sun, Proxima Centauri, at a distance of 4.2 light-years, would take roughly 46 million years of driving. The center of the Milky Way, at about 26,000 light-years, would take roughly 300 billion years. The Andromeda galaxy, at 2.5 million light-years, would take about 28 billion years. The Virgo cluster would take roughly 700 trillion years. The age of the entire universe is only 13.8 billion years. You would need to drive for 50,000 times the age of the universe to reach the nearest galaxy cluster at highway speed, and that cluster is cosmically close. One more comparison to anchor the scale. If the entire observable universe were shrunk to the size of Earth, a sphere roughly 12,700 kilometers in diameter, then a galaxy cluster would be about the size of a small city, a few kilometers across, and the voids between clusters would be oceans, vast stretches of water separating continents. But unlike Earth's oceans, which are full of life and activity, the cosmic voids would be almost perfectly empty, dark, silent, and growing wider every moment. The scientific understanding of these distances has a rich history. The story begins in earnest in the early 20th century, when the true scale of the universe was first revealed. Before 1920, most astronomers believed that the Milky Way was the entire universe. The fuzzy patches of light called nebulae, visible through telescopes, were thought to be clouds of gas within our galaxy. The idea that they might be separate galaxies, island universes in their own right, was debated but not settled. The debate was resolved in 1924 when Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to identify Cepheid variable stars in the Andromeda Nebula. Cepheid stars pulsate with a period that is directly related to their intrinsic brightness, a relationship discovered by Henrietta Swan Leavitt in 1912 at the Harvard College Observatory. By measuring the pulsation period of Cepheids in Andromeda, Hubble could determine their true brightness, and by comparing that to their apparent brightness as seen from Earth, he could calculate the distance. The answer was roughly 900,000 light-years, far beyond the boundaries of the Milky Way. Andromeda was a separate galaxy. This single measurement expanded the known universe by a factor of roughly 10. Suddenly, the cosmos was not one galaxy, but many. Over the following years, Hubble and others measured distances to more and more galaxies, revealing a universe of staggering size. And in 1929, Hubble made his second great discovery. He noticed that the more distant a galaxy was, the faster it appeared to be moving away from us. Its light was shifted toward the red end of the spectrum, stretched by the expansion of space between the galaxy and our telescopes. This relationship, the Hubble-Lemaitre law, provided the first observational evidence that the universe is expanding. The expansion was confirmed and refined over the following decades. In the 1960s, Arno Penzias and Robert Wilson at Bell Labs accidentally discovered the cosmic microwave background radiation, the faint afterglow of the Big Bang, which provided powerful evidence that the universe had once been much hotter, denser, and smaller than it is today. The satellite missions that followed, COBE in 1989, WMAP in 2001, and Planck in 2009, mapped this afterglow with increasing precision, revealing the seeds of cosmic structure in its tiny temperature fluctuations. But the biggest surprise came in 1998, when two teams studying distant supernovae discovered that the expansion of the universe is not slowing down. As most physicists expected, it is speeding up. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Riess, both found that distant Type Ia supernovae were dimmer than expected, meaning they were farther away than a decelerating universe would predict. Something was pushing the universe apart with increasing force. That something was named dark energy. It is not dark matter, and the similarity in names has caused confusion ever since. Dark matter has gravitational attraction, pulling things together, though it does not interact with light. Dark energy is fundamentally different. It is a repulsive influence, a property of space itself that causes the expansion of the universe to accelerate. It makes up roughly 68% of the total energy budget of the universe, making it by far the dominant component of the cosmos. Dark matter contributes about 27%. Ordinary matter, the protons, neutrons, and electrons that make up everything visible, everything you have ever touched, or tasted, or seen, accounts for less than 5%. Every galaxy you have ever seen in a photograph, every star in every constellation you have ever identified on a clear night, every planet in every solar system, every grain of cosmic dust, every atom in every living organism that has ever existed on Earth, all of it combined amounts to less than 1/20th of what the universe contains. The overwhelming majority of reality is invisible, and the largest portion of that invisible majority, dark energy, is the force that controls the distances between galaxy clusters and determines how those distances will evolve across cosmic time. Dark energy is the reason the voids are growing. But here's the problem. Dark energy does not just push, it compounds. Within galaxy clusters, gravity is strong enough to hold things together. The Milky Way and Andromeda are gravitationally bound and are actually falling toward each other at about 110 kilometers per second. They will collide and merge in roughly 4.5 billion years. Within the local group, gravity keeps the galaxies together despite the expansion. But between clusters, where the density of matter drops sharply, gravity loses its battle against expansion. The space between clusters stretches, and dark energy ensures that the stretching accelerates. The analogy cosmologists use most often is raisin bread. Imagine a ball of dough studded with raisins, placed in an oven. As the bread rises, the dough expands uniformly. Every raisin sees every other raisin moving away from it. A raisin near the center sees all the others receding. A raisin at the edge sees exactly the same pattern. No raisin is at the center of the expansion. The expansion happens everywhere, in the dough itself. The raisins are carried along passively. They do not move through the dough. The dough stretches between them. Galaxy clusters are the raisins. Space is the dough. And the oven is dark energy, heating up and making the dough rise faster and faster, with no ceiling, no timer, and no one to turn the oven off. Fritz Zwicky, the eccentric and brilliant Swiss-American astronomer, was among the first scientists to study galaxy clusters with rigorous quantitative methods. Working at the California Institute of Technology in the 1930s, Zwicky turned his attention to the Coma cluster. He observed the individual galaxies within the cluster and measured their velocities by analyzing the Doppler shifts of their light. What he found was deeply puzzling. The galaxies were moving far too fast. Based on the visible matter in the cluster, the amount of stars and gas he could see, there simply was not enough gravitational pull to hold the cluster together. The galaxies should have scattered long ago, flying apart like sparks from a fire that has no hearth. But they had not scattered. The cluster was clearly stable. It had been there for billions of years. Zwicky concluded that there must be far more mass in the cluster than could be seen. He called this hidden mass Dunkel materia, dark matter. His 1933 paper proposing this idea was largely ignored by the astronomical community. It was too radical, too uncomfortable. The notion that most of the mass in a galaxy cluster was invisible seemed almost absurd, but Zwicky was right. He was decades ahead of his time. It was not until the 1970s that his insight was vindicated. The astronomer Vera Rubin, working with instrument maker Kent Ford at the Carnegie Institution of Washington, studied the rotation curves of spiral galaxies. They measured how fast stars at different distances from the center of each galaxy were orbiting. According to Newtonian gravity and the visible matter in the galaxies, stars far from the center should have been orbiting more slowly than stars near the center, much as outer planets in our solar system orbit more slowly than inner ones. But Rubin and Ford found that the orbital velocities remained roughly constant out to the edges of the galaxies. The rotation curves were flat. This was only possible if each galaxy was embedded in a massive halo of invisible matter that extended far beyond the visible disk. Together, Zwicky's cluster observations and Rubin's galaxy rotation curves established that roughly 85% of all matter in the universe is dark matter. It does not emit light, does not absorb light, does not interact with ordinary matter except through gravity. It is invisible to every telescope ever built. But its gravitational influence shapes everything we see. Dark matter is the scaffolding of the cosmic web. It is the invisible skeleton on which galaxy clusters are built. Without it, the clusters would fly apart, the filaments of the cosmic web would dissolve, and the galaxies themselves would be far more diffuse and disordered. Understanding dark matter is essential to understanding the distances between galaxy clusters, because it is dark matter that defines where the clusters are. The dark matter distribution in the universe is not random. It follows the patterns established by quantum fluctuations in the very earliest moments of the universe, during a period called cosmic inflation. These tiny variations in density were amplified by gravity over billions of years. Regions with slightly more dark matter attracted more ordinary matter, grew denser, and eventually became the nodes and filaments of the cosmic web. Regions with slightly less dark matter lost matter to their denser neighbors, grew emptier, and became the voids. The result is the universe we see today, a vast cosmic web of dark matter filaments and nodes, with galaxy clusters sitting at the densest intersections and enormous voids filling the spaces between them. The Sloan Digital Sky Survey, which began observations in the year 2000, has mapped the three-dimensional positions of millions of galaxies, revealing the cosmic web in stunning detail. Galaxies are organized into thin walls and filaments, like the foam in a soap bubble or the structure of a sponge. The voids between these structures are enormous, some spanning hundreds of millions of light-years, and they occupy roughly 80% of the total volume of the observable universe. The cosmic web was predicted, theoretically, before it was fully observed, in the 1970s and 80s. Astrophysicists like Yakov Zeldovich in the Soviet Union and Jim Peebles at Princeton developed mathematical frameworks describing how gravity would amplify small density fluctuations into the large-scale patterns we see today. Computer simulations, such as the Millennium Simulation in 2005 and Illustris TNG in 2018, have confirmed these predictions with striking fidelity, producing virtual cosmic webs that closely match the observed distribution of galaxies. All of these observations and simulations converge on a single, uncomfortable picture. The universe is a vast network of matter concentrated into thin filaments and dense nodes, separated by enormous voids that contain almost nothing. The distances between galaxy clusters, the spaces where the voids are deepest and widest, are the defining features of this network. They are not incidental. They are not secondary. They are the dominant characteristic of the universe's large-scale structure. Most of the volume of the observable universe is void. The clusters and filaments and walls of galaxies are the exception, the rare concentrations in a cosmos that is overwhelmingly empty. And this emptiness is not stable, it is growing. To feel the full weight of this, consider one more comparison. If the entire history of the universe, all 13.8 billion years of it, were compressed into a single calendar year. With the Big Bang at midnight on January 1st and the present moment at midnight on December 31st, then the first stars would have ignited sometime in late January. The Milky Way would have formed around March. The Sun and Earth would have appeared in early September. The dinosaurs would have arrived on December 25th, Christmas Day, and gone extinct on December 30th. The entire history of human civilization would occupy the last few seconds before midnight on December 31st. And the distances between galaxy clusters, measured in hundreds of millions of light years, represent time spans that stretch not just across this calendar year but across dozens, hundreds, even thousands of such years. The light crossing the void between two typical galaxy clusters has been traveling for a significant fraction of the age of the universe. Some of that light has been in transit for longer than the Earth has existed. Now, imagine that same cosmic calendar stretched into the future. The era of stars, the age in which the universe is brightly lit, will last about another 100 trillion years. On the cosmic calendar, that corresponds to about 700,000 more calendar years, and throughout all of those years, the distances between galaxy clusters will continue to grow, the voids will deepen. The filaments will thin, the web will unravel, the darkness will spread, and long before those 700,000 calendar years are done, most galaxy clusters will have crossed the cosmic event horizon and vanished from each other's view forever. The pie chart of the universe's energy budget tells us who is winning this contest. Dark energy, at 68%, is the dominant player. Dark matter, at 27%, provides the gravity that holds clusters together. Ordinary matter, at less than 5%, is almost an afterthought. The structures we admire, the luminous galaxies, the blazing stars, the living planets, are built from the smallest fraction of what exists. And the force that is pulling everything apart is 3 times more powerful than the force holding things together. The outcome is not in question. It is only a matter of time. The voids between galaxy clusters will grow, and every cluster will eventually drift beyond the reach of every other cluster. The connections that currently make the universe a single, interconnected system, a web of matter and energy and light, will be severed one by one. The web will dissolve. The clusters will become islands, and then the islands will be alone. There is something almost paradoxical about this situation. The same force that allows us to see the universe, the fact that light has had 13.8 billion years to travel across expanding space, is also the force that will eventually blind us. Expansion gave light time to reach our telescopes. Accelerating expansion will take that light away. The distances between galaxy clusters are the arena where this paradox plays out. They are large enough for expansion to dominate over gravity, but small enough for now, for light to still cross them. That balance will not hold. The transition from this foundation to the core problem requires one more piece of understanding. The expansion of space has a notable property. It is cumulative. The stretching happens in every region of space simultaneously, and the effects add up over distance. If every megaparsec of space, which is roughly 3.26 million light-years, is expanding at about 67.4 kilometers per second, as current measurements from the Planck satellite suggest, then 2 megaparsecs are separating at about 135 kilometers per second, 10 megaparsecs at 674 kilometers per second, 100 megaparsecs at 6,740 kilometers per second. At a distance of about 14 billion light-years, the cumulative expansion rate exceeds the speed of light. Space beyond that distance is receding faster than light can travel, and no signal emitted from there today will ever reach us. This is the cosmic event horizon, the boundary beyond which the expanding universe hides itself from us permanently. And with every passing moment, more of the universe crosses that horizon and is lost. The distance between galaxy clusters is not a static fact. It is a living, growing, accelerating process, and it carries within it a message about the future of everything. That message is written in the language of expansion, dark energy, and entropy. And it says that the connections between the great structures of the cosmos are temporary. They are fraying, stretching, and will one day break entirely. What comes next is the story of that breaking. The story of how the growing distance between galaxy clusters will reshape the cosmos, erasing connections, destroying knowledge, and leaving every cluster alone in the dark. It is a story written in the mathematics of general relativity, in the physics of an accelerating expansion, and in the cold, precise data from humanity's most powerful telescopes. And it begins with a problem that most people have never heard of, a problem that strikes at the heart of what it means for the universe to have a future at all. The core problem with the distance between galaxy clusters is not simply that it is large. Large distances are common in the universe. Stars are far from each other. Galaxies are far from each other. That is the normal state of things. The problem is that the distance between galaxy clusters is growing, and it is growing in a way that will eventually isolate every cluster from every other cluster. Not temporarily. Not in a way that future technology could bridge. Permanently, irrevocably. The expansion of space between clusters will, given enough time, push those clusters beyond each other's observable horizons. Light from one cluster will never reach another. Signals will become impossible. Knowledge of other clusters will fade, and then vanish, and then be forgotten entirely, with no possibility of recovery. To understand why this is inevitable, we need to examine a subtle but crucial point about the speed of light and the expansion of space. Einstein's special theory of relativity, published in 1905, established that nothing can travel through space faster than light. That speed limit is absolute. No rocket, no signal, no piece of information can move through space faster than 299,792 kilometers per second. This is one of the most thoroughly tested and confirmed principles in all of physics. Nothing travels through space faster than light. But there is a critical distinction here that many people miss. The speed limit applies to objects and signals moving through space. It does not apply to space itself. Space can expand at any rate. There is no cosmic speed limit on the stretching of the fabric of space-time, and when you add up enough stretching over a large enough distance, the cumulative rate of expansion can exceed the speed of light. This sounds like it should be paradoxical, but it is not. No object is moving faster than light. Space is simply being created between objects faster than light can cross it. This is already happening. Right now, at this moment, there are galaxies beyond a certain distance from us that are receding faster than light due to the cumulative expansion of all the space between us and them. We can still see some of those galaxies, but only because the light we are seeing was emitted long ago, when those galaxies were much closer. That old light has been traveling toward us for billions of years, and during its journey, the galaxies that emitted it have continued to recede. New light from those galaxies, light being emitted right now, will never reach us. It is running toward us at the speed of light, but the space between us is expanding faster than the light can cross it. The light is like a person running on a treadmill that is speeding up. No matter how fast they run, they fall farther and farther behind. This defines a boundary called the cosmic event horizon. It is not a physical wall. There is nothing to see, nothing to touch, no surface or barrier. It is a distance beyond which the expansion of space permanently outpaces the speed of light. Any photon emitted from beyond the cosmic event horizon, heading in our direction, will never arrive. It will travel at 300,000 kilometers per second and still fall behind, because every second, the space it must cross grows longer than the distance it covers. The concept of the cosmic event horizon is distinct from the more familiar concept of the observable universe. The observable universe has a radius of about 46.5 billion light-years, measured in terms of the current distance to objects whose light we can see today. This is larger than 13.8 billion light-years because the universe has been expanding while the light traveled. Objects at the edge of the observable universe emitted their light when they were much closer to us, and the expansion of space during the travel time has carried them much farther away. We can still see their ancient light, stretched and dimmed by the expansion, but we can see it. The cosmic event horizon is different. It marks the boundary beyond which no new light will ever reach us. Not ancient light, but light emitted right now. Objects beyond this boundary are receding so fast that any signal they send today will never, in the entire future history of the universe, cross the expanding gap. The current cosmic event horizon sits at roughly 16 billion light-years in terms of proper distance. Everything beyond that distance is already lost to us, at least in terms of new signals. And as the expansion accelerates, the event horizon is actually getting closer. The amount of the universe accessible to new observation is shrinking. This process is subtle but relentless. Imagine a sphere centered on the Milky Way, with its radius at the cosmic event horizon. Today, that sphere encompasses a certain number of galaxy clusters. Tomorrow, the sphere will be very slightly smaller, and some clusters at its outer edge will have slipped beyond it. Next year, more will have slipped beyond. Over hundreds of millions and billions of years, the sphere contracts noticeably, and the number of clusters within it diminishes. One by one, the distant clusters cross the line, and their new light can no longer reach us. The universe does not collapse. It does not get smaller. It gets less visible. Now, here is where this connects directly to galaxy clusters. The expansion of space is not uniform at all scales. On small scales, within galaxies and galaxy clusters, gravity overwhelms the expansion. The Milky Way and Andromeda are actually falling toward each other at roughly 110 kilometers per second and will merge in about 4.5 billion years to form a single, larger galaxy, sometimes called Milkomeda or Milkdromeda. Within the local group, the gravitational bonds between galaxies are strong enough to resist the expansion. The Triangulum Galaxy, the Large and Small Magellanic Clouds, and dozens of smaller dwarf galaxies are gravitationally anchored to the Milky Way and Andromeda. They will not be carried away by expansion. They will stay. Within the Virgo supercluster, gravity has some influence, though the situation is more complicated. The Virgo cluster itself, at the center of the supercluster, exerts a gravitational pull on the local group. Our group of galaxies is falling toward the Virgo cluster at roughly 200 kilometers per second. But it is unclear whether this infall will ever bring us into the Virgo cluster or whether the expansion will ultimately win. The outcome depends on precise measurements of mass, distance, and the Hubble parameter that we do not yet have with sufficient accuracy. What we do know is that beyond the Virgo supercluster, expansion wins decisively. The more distant structures, the Coma cluster, the Perseus cluster, the Shapley concentration, are all receding and will never be reached. But between superclusters, between the great walls and filaments of the cosmic web and the enormous voids that separate them, expansion dominates completely. The gravitational force between two distant galaxy clusters, separated by hundreds of millions of light-years, is far too weak to resist the expansion across that gulf. The clusters are being carried apart by the stretching of space, and the stretching is accelerating. The Hubble parameter quantifies this expansion. It describes the rate at which space is stretching per unit of distance. The current value, as measured by the Planck satellite using observations of the cosmic microwave background, is about 67.4 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years of distance between two objects, the expansion of space adds a recession velocity of 67.4 kilometers per second. There is, however, a significant disagreement about the precise value of the Hubble parameter. Measurements based on the local universe, using Cepheid variable stars and Type Ia supernovae as distance markers, consistently yield a higher value, around 73 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, has persisted for over a decade and has not been resolved. The difference between 67 and 73 may sound small, but over cosmic distances it compounds enormously. At a distance of 1,000 megaparsecs, the difference in recession velocity is roughly 6,000 kilometers per second. The Hubble tension suggests that something is wrong with our assumptions, either about the local measurements, about the cosmic microwave background analysis, or about the cosmological model itself. Some physicists have proposed that the Hubble tension might indicate that dark energy is not constant after all. If dark energy's strength has changed over cosmic time, it could explain the discrepancy between the early universe and late universe measurements. Others have proposed new particles, new interactions, or modifications to gravity. The tension remains one of the most active and contentious debates in modern cosmology. But regardless of which value is correct, the fundamental conclusion is the same. The universe is expanding, the expansion is accelerating, and the distances between galaxy clusters are growing faster and faster. This seems modest at first. 67 kilometers per second is fast by human standards, roughly 240,000 kilometers per hour, but it is tiny compared to the speed of light. However, the key word is per megaparsec. The recession velocity scales with distance. At 10 megaparsecs, the recession velocity is 674 kilometers per second. At 100 megaparsecs, it is 6,740 kilometers per second. At 1,000 megaparsecs, or about 3.26 billion light-years, the recession velocity is 67,400 kilometers per second, roughly 22% of the speed of light. And at about 4,400 megaparsecs, or roughly 14.4 billion light-years, the recession velocity reaches the speed of light. Beyond that distance, space is expanding faster than light. The math is striking. The Virgo cluster, at roughly 20 megaparsecs, is receding at about 1,350 kilometers per second. The Coma cluster, at roughly 100 megaparsecs, is receding at about 6,740 kilometers per second. The Shapley supercluster, at roughly 200 megaparsecs, is receding at about 13,500 kilometers per second. Every distant cluster is moving away from us, and the farther it is, the faster it goes. And because the expansion is accelerating, these recession velocities are increasing over time. This means that galaxy clusters that are currently just inside our observable horizon will eventually cross outside it. Their light will redshift toward infinity, meaning its wavelength will stretch longer and longer until it becomes undetectable by any instrument. Their images will freeze and fade, growing dimmer and redder until they vanish from the sky as though they never existed. This fading is not instantaneous. It is a gradual process that unfolds over billions of years. A galaxy cluster near the edge of our cosmic event horizon does not suddenly blink out. Instead, its light stretches, decade by decade, century by century, millennium by millennium. The visible light shifts to infrared, the infrared shifts to microwave, the microwave shifts to radio. The radio waves stretch to wavelengths longer than the Earth, longer than the orbit of Jupiter, longer than the solar system itself. Eventually, the wavelength becomes so long that no physical detector could ever absorb a single oscillation. The cluster fades not into blackness, but into wavelengths so stretched that the concept of light ceases to have practical meaning. Meanwhile, the cluster's image slows down. Due to the relativistic effects of the expansion, time appears to slow for receding objects. Events that take 1 second in the cluster's own frame take longer and longer as seen from our perspective. The cluster appears to freeze, its galaxies hanging motionless in a dimming, reddening glow, until the last traces of its light fade below any threshold of detection. It dies not with a dramatic exit, but with an infinite slow-motion fade, stretching its final photons across an eternity of expansion. This process is not speculative. It is not based on uncertain models or controversial assumptions. It is a direct, unavoidable consequence of the measured acceleration of cosmic expansion. It is happening now. 2. It will continue, and its ultimate outcome is a universe in which our local group, the small collection of galaxies gravitationally bound to the Milky Way, is the only visible structure in the sky. Everything else will have been swallowed by the expansion. Every other cluster, every other supercluster, every other wall and filament and node of the cosmic web will have drifted beyond the horizon. The night sky, aside from the stars of our own galaxy, will be perfectly black. Not the black of a cloudy night with stars hidden behind clouds, the black of genuine emptiness, the black of a universe that, from our perspective, contains nothing else. The history of this understanding stretches back more than a century. As early as 1917, the Dutch astronomer Willem de Sitter proposed a model of the universe driven by a cosmological constant, a form of energy inherent in empty space. Einstein had introduced the cosmological constant into his field equations of general relativity in order to produce a static universe, one that neither expanded nor contracted. At the time, a static universe was the prevailing assumption. But De Sitter showed that a universe with a cosmological constant and very little matter would expand exponentially, growing faster and faster without end. Einstein eventually abandoned the cosmological constant after Hubble's discovery that the universe is expanding, famously calling it his greatest blunder. For decades, the cosmological constant was treated as a historical curiosity, an unnecessary complication in the equations of cosmology. Most physicists assumed it was zero. The universe was expanding, but gravity was slowing it down, and the only question was whether the expansion would continue forever or eventually reverse into a contraction. 3 possible futures were debated throughout the middle decades of the 20th century. If the universe contained enough matter, its gravity would eventually halt and reverse the expansion, leading to a big crunch, a fiery collapse back to a singular point. If it contained less matter, the expansion would slow but never stop, continuing forever at an ever-decreasing rate. And if the density was exactly at the critical value, the expansion would asymptotically approach zero velocity but never quite stop. All 3 scenarios assumed that gravity was the only force acting on the expansion, and that the expansion was necessarily decelerating. The discovery in 1998 overturned all of this. The expansion was not decelerating, it was accelerating. None of the 3 traditional scenarios was correct. Something else was at work, something that pushed the expansion faster rather than allowing gravity to slow it down. The cosmological constant, Einstein's blunder, came roaring back as the simplest and most natural explanation. The simplest explanation for dark energy was exactly what De Sitter had described decades earlier: a constant energy density built into the vacuum of space. Every cubic meter of space has a tiny amount of energy in it, and as space expands and new cubic meters appear, the total energy grows, driving the expansion even faster. The discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, but the prize came with an uncomfortable truth. If the cosmological constant is real, if dark energy truly is a permanent, unchanging property of the vacuum, then the accelerating expansion will never stop. There is no mechanism in known physics that could turn it off. The future of the universe is not a gentle coast to equilibrium. It is an endless, accelerating stretch into emptiness. The value of this vacuum energy is extraordinarily small. It corresponds to roughly 6.3 times 10 to the negative 30 joules per cubic meter. That is an almost inconceivably tiny number. If you could somehow collect the dark energy from a cubic meter of space, you would have less energy than the heat from a single breath on a cold morning. But there are an incomprehensible number of cubic meters in the universe, and the total effect is overwhelming. Dark energy's cumulative influence far exceeds gravity on the largest scales. And it gets worse. The vacuum energy does not dilute as the universe expands. This is the crucial difference between dark energy and every other form of energy in the cosmos. When ordinary matter expands, it spreads out and becomes less dense. If you double the volume of a box of gas, the density of the gas halves. This is intuitive. It makes physical sense. Radiation also dilutes, and it loses additional energy because its wavelength stretches as space expands. A photon in an expanding universe becomes redder and less energetic over time. Both matter and radiation become less important as the universe grows. But vacuum energy, if it truly is a cosmological constant, obeys entirely different rules. Its density remains the same no matter how much space there is. This is not intuitive. It seems to violate the principle that things spread out as they expand. But vacuum energy is not a substance distributed through space. It is a property of space itself. Every cubic meter of vacuum has the same energy density, regardless of how many cubic meters exist. When space expands and new cubic meters are created, each new cubic meter arrives with its own vacuum energy already included. The density stays constant. But the total amount of vacuum energy increases because there is more space containing that constant density. And more total dark energy means a stronger push, which means faster expansion, which means more space, which means more total dark energy. It is a self-reinforcing cycle with no natural stopping point, no built-in brake, no inherent limit. The expansion will continue to accelerate as long as the cosmological constant remains positive, and there is no known physical mechanism that could change it. The distances between galaxy clusters will continue to grow faster and faster forever. Astronomers have mapped the large-scale consequences of this process with extraordinary precision. The Sloan Digital Sky Survey has catalogued the positions and redshifts of millions of galaxies, producing three-dimensional maps of the cosmic web. The 2-degree field galaxy redshift survey, completed in 2003, mapped over 220,000 galaxies in the southern sky. The 6-degree field galaxy survey extended this to the entire southern hemisphere. And the Dark Energy Spectroscopic Instrument, DESI, which began survey operations in 2021 at the Kitt Peak National Observatory in Arizona, is measuring the positions of tens of millions of galaxies and quasars to create the most detailed map of the universe's expansion history ever constructed. These surveys have revealed the full extent of the voids between galaxy clusters. The Boyter's Void, discovered in 1981, spans 330 million light-years with almost nothing in it. Within that enormous volume, you could fit 1,000 Milky Way galaxies side by side and still have room to spare. Yet the void contains only about 60 galaxies, scattered like a handful of pebbles in an empty warehouse. The giant void, identified in 2004 in data from the WMAP satellite, spans roughly 1.3 billion light-years. The cold spot, a region of the cosmic microwave background that is slightly colder than its surroundings, may be associated with a supervoid along the line of sight, a region of lower than average density stretching across billions of light-years. The KBC void, within which our own Milky Way resides, spans roughly 2 billion light-years. This means that we are not living in a typical region of the universe. We are living in an underdensity, a region where the average matter content is lower than the cosmic mean. The galaxies around us are slightly more spread out, the space slightly emptier than what you would find in a typical random location in the cosmos. We are desert dwellers, though the desert is so vast that from our perspective, it looks like the whole universe. Between every major galaxy cluster, there are voids of varying sizes, typically ranging from 100 million to 300 million light-years across. Some are rounder, more like bubbles. Others are more elongated, stretched along the boundaries between filaments. Recent surveys suggest that voids occupy roughly 60 to 80% of the total volume of the observable universe. The bright, bustling clusters and filaments that we photograph and study are the minority. The majority of the cosmos is empty, quiet, dark, and expanding. These are the spaces where expansion runs unchecked, where gravity has no grip, where dark energy reigns, and they are growing. Every year, the voids expand by a tiny but measurable amount. Over billions of years, those tiny increments accumulate into a profound transformation of the cosmic landscape. The voids are not simply static regions of emptiness, they are dynamic, evolving structures. As matter drains out of them, pulled by the gravity of nearby filaments and clusters, the voids become even emptier, and as they become emptier, the gravitational forces within them weaken, allowing expansion to proceed even faster. The voids feed on themselves, their emptiness enabling more emptiness, their growth enabling more growth. This has been observed directly. Surveys of the local universe show that galaxies near the edges of voids are moving outward, pushed by the expansion and pulled by the denser structures that border the void. The Hubble flow, the overall expansion of space, is slightly faster inside voids than outside them, because there is less matter to resist it. Voids are not just empty. They are actively emptying, pushing their remaining contents toward the walls and filaments that surround them, like a bathtub slowly draining the last of its water. The implications for galaxy clusters are direct. As the voids grow, the filaments that connect clusters thin and weaken. Less matter flows along those filaments toward the clusters, reducing the rate at which clusters can grow and accrete new material. The clusters that exist today are, for the most part, the clusters that will exist forever. few new massive clusters will form in the future. The assembly line of cosmic structure has slowed nearly to a halt, starved of raw material by the expanding voids. The cosmic microwave background, the afterglow of the Big Bang, provides a snapshot of the universe when it was only 379,000 years old. At that time, the universe had cooled enough for atoms to form, and the fog of free electrons that had made the cosmos opaque suddenly cleared, releasing a flood of light that has been traveling through space ever since. That light, now redshifted to microwave wavelengths, fills the entire sky with a faint, nearly uniform glow. Its temperature is about 2.725 degrees above absolute zero, making it the coldest naturally occurring temperature that can be measured in the cosmos. But the cosmic microwave background is not perfectly uniform. There are tiny fluctuations in its temperature, variations of about 1 part in 100,000. These fluctuations are the fingerprints of density variations in the early universe. Regions that were slightly denser than average appear slightly warmer. Regions that were slightly less dense appear slightly cooler. These density variations, amplified by gravity over billions of years, became the structures we see today. The denser regions collapsed into the filaments and nodes of the cosmic web, where galaxy clusters formed. The less dense regions expanded and emptied, becoming the voids. The seeds of the great emptiness between galaxy clusters were planted in the first moments after the Big Bang, during an epoch called cosmic inflation. In the first tiny fraction of a second after the Big Bang, roughly 10 to the negative 36 seconds, the universe underwent a period of exponential expansion so violent and so rapid that it defies comprehension. In a time interval shorter than anything measurable by any clock, the universe expanded by a factor of at least 10 to the 26th power. A region smaller than a proton was stretched to a size larger than the current observable universe. This inflation was driven by a hypothetical field called the inflaton, whose energy density briefly dominated all other forms of energy. During inflation, quantum fluctuations in the inflaton field, the random, inherent uncertainty that exists in all quantum systems, were stretched from subatomic scales to cosmic scales. These fluctuations became variations in the density of matter and energy across the universe. Some regions ended up with very slightly more energy than average. Others ended up with very slightly less. The differences were minute, roughly 1 part in 100,000, but they were enough. Gravity amplified them relentlessly over the following billions of years. The denser regions attracted more matter. Their gravity pulled in gas and dark matter from the surrounding space, growing denser and denser over time. Eventually, they became dense enough to collapse, forming the first stars, the first galaxies, and eventually the galaxy clusters and filaments of the cosmic web. The less dense regions, by contrast, lost matter to their denser neighbors. Gas and dark matter flowed out of these regions, drawn away by the gravitational pull of the growing structures nearby. These depleted regions became the voids. So the distance between galaxy clusters is not arbitrary. It is not random. It was set by quantum mechanics, by the random fluctuations of a field in the first fraction of a second of existence, amplified by gravity across 13.8 billion years, and then stretched further by the accelerating expansion, driven by dark energy. The voids between clusters are fossil structures, ancient relics of the quantum uncertainty that existed at the birth of the cosmos, now grown to monstrous size by billions of years of gravitational sculpting and dark energy expansion. And then, about 5 billion years ago, dark energy took over. Matter, which had been the dominant component of the universe's energy budget for billions of years, was diluted by the expansion until its density fell below that of dark energy. Dark energy, with its constant density, became the dominant force. The expansion shifted from decelerating to accelerating, and the voids, which had been growing slowly under the influence of gravity alone, began to expand faster under the additional push of dark energy. The scientists who have studied this process most carefully have reached a consistent conclusion. The cosmic web is a temporary structure. It exists because matter has had enough time to flow along gravitational gradients and concentrate into filaments and clusters, but dark energy has not yet had enough time to rip those structures apart. We live in a transitional era, an era when the web still exists, when clusters are still connected by filaments, when light from distant structures can still reach us. But this era will not last. Consider a photon traveling between two galaxy clusters separated by a void 500 million light-years across. That photon, traveling at the speed of light, would take 500 million years to cross the void. But during those 500 million years, the void would expand. The photon would arrive at its destination, but the clusters would be farther apart than when it began its journey. The next photon emitted would have an even longer journey, and the next one longer still. Eventually, after enough time, the expansion of the void would outpace the photons entirely. No more light would cross the gap. The clusters would become invisible to each other. For many galaxy clusters, this process is well underway. Clusters at the edges of our observable universe are already fading from view. Their light is redshifting toward infinity. Their images are dimming. They are slipping across the cosmic event horizon, and once they cross it, no future observation, no matter how sensitive, will ever detect them again. The concept was explored with devastating clarity in a paper published in 2007 by the physicists Lawrence Krauss of Arizona State University and Robert Scherer of Vanderbilt University. Their paper, titled The Return of a Static Universe and the End of Cosmology, described what the universe would look like to observers in the far future. They showed that in a universe dominated by dark energy, future civilizations would have no observational evidence for the Big Bang. The cosmic microwave background would have redshifted to undetectable wavelengths. The distant galaxies would have faded beyond the sensitivity of any conceivable instrument. The expansion of the universe would be unmeasurable because there would be no distant objects to serve as reference points. Those future observers would look out and see only their own local cluster of galaxies. They would see no evidence that other clusters had ever existed. They would have no way to discover the cosmic microwave background, no way to measure the Hubble parameter, no way to infer the existence of dark energy. The entire intellectual edifice of modern cosmology, from the discovery of the expanding universe to the measurement of the accelerating expansion, would be inaccessible to them. Not because they were less intelligent, but because the evidence would have been erased. The expansion itself would have destroyed the information needed to understand it. They would develop a cosmology that was sophisticated and internally consistent but fundamentally wrong. They would conclude that the universe was static, that it consisted of a single cluster of galaxies in an infinite void, that it had always been this way and would always be this way. They would have no reason to suspect otherwise, because all the evidence to the contrary would have been carried beyond the horizon by the very expansion they could not detect. Their textbooks would describe a universe that bore no resemblance to the real one. Their theories would be self-consistent, testable, and wrong, not because of any failure of intelligence or method, but because the data they needed had been stolen by the expansion of space. Krauss and Scherer noted that even the energy content of the local cluster would eventually mislead future scientists. They would observe the cluster's mass and motion, but they would attribute it entirely to ordinary and dark matter. They would have no reason to suspect the existence of dark energy, because the only way to detect dark energy is to observe the recession of distant objects, and there would be no distant objects to observe. The most important component of the universe, the force driving its evolution, would be invisible and undetectable. The universe would have hidden its deepest secret behind an impenetrable wall of expanding space. This is perhaps the most disturbing aspect of the distance between galaxy clusters. It is not just a physical separation, it is an informational one. The growing voids are not just pushing clusters apart. They are destroying knowledge. They are erasing the record of the universe's history, concealing its true size, its true age, and its true nature from anyone who arrives too late to see the evidence. But here's what makes this truly terrifying. We may already be in the early stages of this erasure. The information available to us right now, in this particular epoch of cosmic history, may be the most we will ever have. We live in a privileged era, a brief cosmic window when the universe is young enough for its structures to be visible and comprehensible. Every moment that passes, more light crosses the cosmic event horizon and is lost forever. More galaxies fade from view. More of the cosmic web becomes invisible. The window of knowledge is finite, and it is closing. The astronomer Abraham Loeb of Harvard University has emphasized this point. He has argued that we are living in the golden age of observational cosmology. Not because our instruments are the best they will ever be, but because the sky is the most informative it will ever be. Future civilizations will have better telescopes, better detectors, better mathematics. But they will have less to look at. The data will have been carried away by the expansion. The universe will still be there, but it will have hidden itself. There is a painful irony in this. We often think of scientific knowledge as cumulative, always increasing, always deepening. In most domains, this is true. Each generation of scientists builds on the work of the previous one, climbing higher on an ever-growing edifice of understanding. But cosmology may be the exception. In cosmology, the raw data, the light from distant galaxies, the cosmic microwave background, the observable expansion of space, these are being consumed by the expansion. The data set is shrinking. The evidence is disappearing. We are the generation with the most cosmological information available, and future generations will have less. This is not a slow, distant process. The timescale is long by human standards, tens of billions of years, but it is short by cosmic standards. The universe is 13.8 billion years old. In roughly 100 billion years, a span of time only about 7 times greater than the current age of the universe, the cosmic microwave background will have redshifted below the detection threshold of even the most sensitive instruments imaginable. In roughly 2 trillion years, all galaxies outside the local group will have crossed the event horizon. The night sky will contain only the stars of our own merged galaxy, a single island of light in an infinite ocean of darkness, with no trace of anything beyond. To feel the weight of these timescales, consider this comparison. If the current age of the universe were represented by a single year, the era in which the cosmic microwave background remains detectable would last about another 7 years, and the era in which other galaxy clusters remain visible would last about another 145 years. Those sound like long times when measured in years, but compared to the future duration of the universe, which under the standard model extends to infinity, they are nothing. They are the first few heartbeats of a life that will last forever, and after those heartbeats, the evidence is gone. The distances between galaxy clusters are the front lines of this process. They are where the expansion is winning. They are where the light is fading. They are where the connections between the great structures of the cosmos are being stretched past their breaking points, and they carry a message that is both profound and deeply unsettling. The universe is not just expanding, it is forgetting. It is erasing its own history, one galaxy cluster at a time, leaving behind an ever smaller record of its former grandeur. And the erasure cannot be stopped, because the force driving it is built into the fabric of space itself. We stand at a unique moment in cosmic history. The voids are wide enough to see across. The microwave background is still detectable. The galaxy clusters are still connected by thin filaments of matter that light can traverse. We can still count the clusters, map the web, measure the expansion. We can still know what the universe truly looks like. But the distances between galaxy clusters are growing. The filaments are thinning. The horizons are closing in. And the question that hangs over everything, the question that every observation of the cosmic voids forces us to confront, is this: what can be done about it? Is there any theory, any force, any mechanism that could halt the expansion, bridge the growing gaps, or preserve the connections between clusters? Is there any escape from the isolation that the accelerating expansion promises? That is what we turn to next: the attempts to understand, to quantify, and to confront the growing emptiness between the galaxy clusters, the theories, the measurements, the simulations, and the sobering conclusions they have produced. The problem of the growing distance between galaxy clusters has occupied some of the most capable minds in physics and cosmology for more than 2 decades. Since the discovery of the accelerating expansion in 1998, scientists have pursued multiple avenues of investigation, each aimed at understanding the expansion more precisely, identifying its cause, and exploring whether anything could counteract it. These efforts have produced important insights. They have also produced a deepening sense that the expansion is a fundamental and permanent feature of the cosmos, not a phase that will pass or a puzzle that will be solved. The first approach, and the most direct, is precision measurement. How do we actually know how far apart galaxy clusters are? How do we know the distances are growing? And how do we know the growth is accelerating? The answers involve a carefully constructed chain of techniques known as the cosmic distance ladder. This is not a single measurement method, but a sequence of methods, each calibrated against the one before it, that allows astronomers to reach farther and farther into the cosmos with quantified confidence. The first rung of the ladder is trigonometric parallax. As the Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars, just as your thumb appears to jump from side to side when you look at it with alternating eyes. By measuring the angle of this shift, and knowing the diameter of the Earth's orbit, astronomers can calculate the distance to nearby stars using basic geometry. The European Space Agency's Gaia spacecraft, launched in 2013 and still operating, has measured parallax angles for nearly 2 billion stars with extraordinary precision, establishing accurate distances to stars as far as tens of thousands of light-years from Earth. Gaia has provided the most precise three-dimensional map of our galaxy ever constructed. The second rung involves Cepheid variable stars. These are giant, pulsating stars whose brightness oscillates with a period that is directly related to their intrinsic luminosity. A Cepheid that pulsates once every 30 days is intrinsically brighter than one that pulsates every 3 days, and the relationship is precise and predictable. By measuring how quickly a Cepheid pulsates, astronomers can determine how bright it truly is. Then, by comparing that intrinsic brightness to how bright it appears from Earth, they can calculate the distance. This technique was pioneered by Henrietta Swan Leavitt, who in 1912 published her discovery of the period-luminosity relationship based on Cepheids in the Small Magellanic Cloud. It remains one of the most powerful tools in extragalactic astronomy. The Hubble Space Telescope, launched in 1990, spent years calibrating Cepheid distances to galaxies as far as 100 million light-years away through a program called the Key Project, led by Wendy Friedman. The third rung is Type Ia supernovae. These are thermonuclear explosions that occur in binary star systems when a white dwarf star, the dense remnant of a sun-like star, accretes matter from a companion until it reaches a critical mass of about 1.4 solar masses, known as the Chandrasekhar limit. At that point, the white dwarf undergoes a runaway nuclear detonation, producing a brilliantly luminous explosion that can outshine an entire galaxy for several weeks. Because the triggering condition is always the same, roughly the same mass reaching roughly the same critical point, the peak brightness of these explosions is highly consistent, making them excellent standard candles. They can be detected at distances of billions of light-years, far beyond the reach of Cepheids. It was Type Ia supernovae that provided the crucial evidence for the accelerating expansion. In 1998, the two competing teams, the Supernova Cosmology Project and the High Z Supernova Search Team, measured the distances and redshifts of dozens of distant Type Ia supernovae. The supernovae were dimmer than expected. They were farther away than a decelerating universe would predict. The only explanation was that the expansion had been accelerating, pushing the supernovae to greater distances than anticipated. This discovery did not happen overnight. It required years of painstaking observation, careful calibration, and meticulous analysis. Each supernova had to be identified, confirmed, observed photometrically and spectroscopically, and compared against a database of well-characterized nearby supernovae. The teams used some of the most powerful telescopes in the world, including the Keck telescopes in Hawaii and the telescopes at Cerro Tololo in Chile. The analysis required accounting for the absorption of light by dust in both the host galaxy and the Milky Way, for possible evolutionary changes in supernovae properties over cosmic time, and for the peculiar velocities of host galaxies relative to the smooth Hubble flow. The result was unambiguous. Both teams, working independently and using different datasets and analysis methods, reached the same conclusion. The expansion was accelerating. The universe was not doing what anyone had expected, and the force responsible for the acceleration was unlike anything in the standard toolbox of physics. It was not gravity. It was not electromagnetism. It was not the strong or weak nuclear force. It was something new, something strange, something that lived in the vacuum itself. Beyond supernovae, additional techniques extend the reach of the distance ladder even further. The Tully-Fisher relation, developed by Brent Tully and Richard Fisher in 1977, connects a spiral galaxy's rotation speed to its intrinsic luminosity. Faster rotating galaxies are more luminous. By measuring the rotation speed, typically through radio observations of hydrogen gas, and comparing the predicted luminosity to the observed brightness, the distance can be determined. A similar technique, the Faber-Jackson relation, works for elliptical galaxies, connecting their stars' velocity dispersion to luminosity. The Sunyaev-Zeldovich effect provides a completely independent distance measurement for galaxy clusters. When photons from the cosmic microwave background pass through the hot gas in a galaxy cluster, they interact with the high-energy electrons in that gas through a process called inverse Compton scattering. This shifts the photons to slightly higher energies, creating a distinctive distortion in the microwave background at the location of the cluster. By comparing the magnitude of this distortion to the X-ray brightness of the cluster gas, astronomers can calculate the physical size of the cluster and thus its distance. This method is particularly valuable because it is independent of the other rungs of the distance ladder and provides a direct check on their results. Each of these methods has its own uncertainties, its own assumptions, and its own potential sources of error. When different methods give different answers, it reveals a problem. And right now, there is a significant problem. The Hubble tension, the disagreement between the expansion rate measured from the cosmic microwave background, about 67.4 kilometers per second per megaparsec, and the rate measured from the local distance ladder, about 73 kilometers per second per megaparsec, remains unresolved. Despite years of effort, improved calibrations, and alternative measurement strategies, the tension has not gone away. It has, if anything, grown sharper. The tension matters for our topic because the precise value of the Hubble parameter determines how fast the voids between galaxy clusters are expanding and how quickly the cosmic event horizon is closing in. A higher Hubble parameter means faster expansion, a faster closing horizon, and a shorter window of observational accessibility. A lower value means a slightly longer window. The difference between 67 and 73 may sound small, but projected over billions of years, it changes the timeline of cosmic isolation significantly. To illustrate, consider the most distant galaxy cluster currently detectable. At a Hubble parameter of 73, that cluster's light would redshift below detectability roughly 10% sooner than at a parameter of 67. Over the next 50 billion years, this difference compounds. The accelerating expansion is exponential, and small differences in the exponential rate produce large differences in outcome. At a parameter of 73, the observable universe shrinks noticeably faster, the event horizon closes in more rapidly, and the era of cosmic visibility ends sooner. Something is wrong with our assumptions. Either our measurements of the local expansion rate are subtly biased by unrecognized systematic effects, perhaps dust, calibration errors, or peculiar velocities of nearby galaxies, or our interpretation of the cosmic microwave background data relies on model assumptions that are not quite right. Or, most tantalizingly, the standard cosmological model itself is incomplete. Perhaps there are new particles, new forces, or new physics operating in the early universe that change how the cosmic microwave background data should be interpreted. Several proposals have been made, including early dark energy, interacting dark matter, additional neutrino species, and modifications to the theory of inflation. None has yet provided a fully satisfactory resolution. The Hubble tension is not an academic curiosity, it is a crack in the foundation of modern cosmology. And until it is resolved, our predictions for the future of the distances between galaxy clusters carry an additional layer of uncertainty. We know the clusters are separating. We know the separation is accelerating. But the precise rate, and therefore the precise timeline, remains in question. The second major approach has been through computer simulation. Modern cosmological simulations are among the most computationally intensive projects in all of science, requiring millions of processor hours on the world's largest supercomputers. They model the evolution of matter and energy from the smooth, nearly uniform conditions of the early universe to the complex, structured cosmos we observe today. The Millennium Simulation, run in 2005 by the Virgo Consortium led by Volker Springel and colleagues, was a landmark in this field. It tracked the gravitational evolution of more than 10 billion particles of dark matter within a cubic volume 1.9 billion light-years on a side. The simulation started from initial conditions matched to the cosmic microwave background and ran forward in time for 13.8 billion years, producing a detailed model of how the cosmic web formed. The result was a strikingly realistic cosmic web with clusters at the nodes, filaments connecting them, and voids filling the spaces between. The Millennium Simulation was followed by increasingly sophisticated successors. The illustrious TNG project, completed in 2018, added gas dynamics, star formation, magnetic fields, and the feedback from supermassive black holes. The resulting virtual universe contained millions of galaxies with realistic morphologies, luminosities, and chemical compositions. The Uchu simulation, completed in 2021, was even larger, modeling 2.1 trillion particles of dark matter across a volume 9.6 billion light-years on a side, making it one of the largest cosmological simulations ever run. These simulations reveal a consistent and troubling picture. The voids are winning. As the universe ages and dark energy becomes more dominant, the filaments thin, the walls dissolve, and the voids expand. Matter drains from the voids into the filaments, and from the filaments into the clusters, but the supply is dwindling. The rate at which clusters accrete new material has dropped sharply over the last several billion years and will continue to decline. To visualize what the simulations show, imagine watching a time-lapse of the cosmic web across billions of years. In the early frames, the web is dense and dynamic. Filaments are thick with flowing matter. Clusters at the intersections are growing rapidly, accreting galaxies and gas from all directions. The voids are relatively small and compact, squeezed between vigorous filaments. As the frames advance and dark energy becomes dominant, the change is subtle at first. The filaments begin to thin. The flow of matter along them slows. The voids begin to expand, imperceptibly at first, then noticeably. The edges of the voids push outward, their boundaries retreating from the clusters. The filaments become wispy, like threads being pulled from a fabric. Some of the thinnest filaments break entirely, their matter drawn into the nearest cluster, leaving nothing but expanding void where a connection once existed. In the later frames, the web is unrecognizable. The elaborate network of filaments and walls and nodes has been replaced by scattered, isolated clumps of matter, like islands left behind as an ocean drains. Each clump is a galaxy cluster, massive and ancient, containing thousands of galaxies and trillions of stars, but utterly alone. The space between the clumps is not merely empty. It is actively expanding, pushing the clumps apart at accelerating speeds, ensuring that no bridge between them can ever be rebuilt. When these simulations are run forward to 100 billion years from now, roughly 7 times the current age of the universe, the cosmic web has largely dissolved. The filaments that connect clusters today have been stretched beyond recognition. The walls have evaporated. The voids have merged into a single, all-encompassing emptiness broken only by isolated clusters, each surrounded by its own halo of dark matter, but cut off from every other cluster by expanding space. The simulations paint a picture of a universe that is slowly but surely going dark, its structures dispersing like a sandcastle dissolving under a rising tide. The numbers are striking. In the current epoch, roughly 20% of the volume of the observable universe is occupied by filaments, walls, and clusters. 80% is void. By 100 billion years from now, the fraction occupied by structures will have shrunk to a few percent. By 1 trillion years, the concept of a cosmic web will be meaningless. There will be no web. There will be isolated nodes in a featureless expanse. The simulations also reveal a detail that is easy to overlook. As the cosmic web dissolves, the remaining isolated clusters do not simply sit unchanged. They continue to evolve internally. Galaxies within them merge with each other, their stars mixing into ever larger, more amorphous elliptical galaxies. The gas between galaxies cools and falls into the cluster center, or is heated by feedback from active galactic nuclei and expelled to the outskirts. Black holes grow by swallowing gas and merging with other black holes. The internal evolution of a cluster is rich and complex, even as its external connections to the cosmic web are severed. But internal evolution cannot replace external supply. A cluster that is cut off from the cosmic web is a closed system, at least in terms of matter. It will never gain new galaxies, new gas, or new dark matter from outside. Everything it will ever have is already within its gravitational reach. This is fundamentally different from the universe we live in today, where clusters are still growing, still accreting, still connected to the web by active filaments. The transition from an open, connected cluster to a closed, isolated one is gradual, but it is relentless, and it is driven by the growing distances between clusters. The third approach has explored whether any physical mechanism could counteract the expansion between clusters. Could gravity, given enough time and enough mass, pull clusters back together? Could some unknown force reverse the expansion? Could a new theory of physics rescue the cosmic web from dissolution? The answer, based on current knowledge, is no. For gravity to overcome the expansion between two galaxy clusters, the gravitational attraction between them would need to exceed the expansion rate across their separation. This is calculable. The gravitational force between two objects decreases with the square of the distance between them. The expansion rate increases linearly with distance. At small separations, gravity can win. At the scale of galaxy groups and small clusters, gravity holds things together against the expansion. The Milky Way and Andromeda, separated by only 2.5 million light-years, are falling together despite the expansion. But at separations of hundreds of millions of light-years, the expansion is overwhelming. Consider two galaxy clusters separated by 300 million light-years, each with a mass of 1 quadrillion solar masses. The gravitational acceleration between them is minuscule, roughly 10 to the negative 14 meters per second squared, about 1 trillion times weaker than the gravitational pull of a grain of sand held in your hand. The expansion, by contrast, adds recession velocity at a steady rate that compounds with distance. Gravity cannot overcome it. The clusters will drift apart, and the drifting will accelerate. To put this in another scaled comparison, imagine the gravitational force between two galaxy clusters as a thread connecting two ships at sea. The thread represents the gravitational attraction. It is real. 2. It is there, but it is impossibly thin, impossibly weak, and the current of the expanding ocean is pulling the ships apart with a force that makes the thread irrelevant. The ships are connected, technically, but the connection does nothing. The current is too strong, the distance is too great. The thread will not pull the ships together. It will simply stretch and thin until it might as well not exist. This is the situation between every pair of galaxy clusters separated by more than a few tens of millions of light-years. Gravity connects them, but the connection is functionally meaningless. The expansion is in charge, and it is accelerating. Some physicists have explored the possibility that dark energy might not be a true cosmological constant. If dark energy is instead a dynamic field, sometimes called quintessence, its energy density could change over time. In some quintessence models, dark energy weakens over cosmological timescales, allowing gravity to gradually reassert itself. In more exotic models, dark energy could even become negative, turning from a repulsive force to an attractive one, potentially halting or reversing the expansion. Observational programs have been designed specifically to test these possibilities. The Dark Energy Survey, which operated from 2013 to 2019, using the Victor Blanco 4-meter telescope at the Cerro Tololo Inter-American Observatory in Chile, mapped the distribution of hundreds of millions of galaxies across a large swath of the southern sky. It measured the clustering of galaxies, the distortion of galaxy shapes by gravitational lensing, and the distance redshift relationship of type Ia supernovae, all to constrain the properties of dark energy. The Dark Energy Spectroscopic Instrument, or DESI, is the next generation of this effort, installed at the Male 4-meter telescope at Kitt Peak National Observatory in Arizona. DESI began its 5-year survey in 2021. It is measuring the redshifts of roughly 40 million galaxies and quasars, mapping the expansion history of the universe over the last 11 billion years with percent-level precision. Its goal is to determine whether dark energy is constant or evolving. Early results from DESI, released in 2024, generated significant excitement. The data showed slight deviations from the predictions of a pure cosmological constant, hinting that dark energy's influence might have changed over cosmic time. Specifically, the data suggested that dark energy might have been weaker in the past and stronger now, or possibly the reverse, depending on the model used to interpret the results. The deviations were modest and not yet statistically definitive, hovering around the 2 to 3 sigma level, which is suggestive but not conclusive. In physics, a 5 sigma result is generally required to claim a discovery. The DESI hints are intriguing, but they are not yet discoveries. More data from the ongoing survey will be needed to determine whether the hint is real or a statistical fluctuation. If the hints are confirmed, they could reshape our understanding of dark energy and, by extension, the future of the distances between galaxy clusters. A dark energy that changes over time could behave very differently from a cosmological constant. In some models, dark energy could weaken, allowing gravity to slow the expansion on the largest scales. In others, it could strengthen, accelerating the expansion even faster than the standard model predicts. In the most dramatic scenarios, dark energy could eventually become so strong that it tears apart not just the cosmic web, but galaxy clusters themselves, galaxies, stars, planets, and ultimately even atoms, in a catastrophic event called the Big Rip. The Big Rip was proposed by the physicist Robert Caldwell and colleagues in 2003, and remains a theoretical possibility, though most current observations disfavor it. The European Space Agency's Euclid mission, launched in July of 2023, is providing complementary data. Euclid is surveying roughly a third of the sky in visible and near-infrared light, measuring the shapes and positions of billions of galaxies to map the distribution of dark matter through gravitational lensing and the expansion history through galaxy clustering. Together, DESI and Euclid are expected to provide the most stringent tests of dark energy yet attempted. The Nancy Grace Roman Space Telescope, planned for launch by NASA, will add further constraints through its own surveys of supernovae, gravitational lensing, and galaxy clustering. But even if dark energy turns out to be variable, the implications for galaxy cluster isolation are not fundamentally altered. For the expansion between clusters to halt, dark energy would need to decrease dramatically, essentially vanishing or turning negative. No current observational data support such a dramatic change. The hints from DESI suggest, at most, modest variability. The change needed to save the cosmic web from dissolution is of an entirely different magnitude. It would require dark energy to behave in a way that contradicts every measurement made so far. The fourth approach comes from an unexpected direction. Some cosmologists have asked whether the distances between galaxy clusters might contain information about the fundamental physics of spacetime itself. This line of inquiry connects the largest scales of the universe to some of the deepest questions in theoretical physics. One avenue involves modified gravity theories. The standard cosmological model assumes that Einstein's general relativity is the correct description of gravity on all scales. But what if gravity behaves differently on the largest scales, the scales of galaxy clusters and cosmic voids? Modified gravity theories, such as FR gravity, propose changes to Einstein's equations that could mimic the effects of dark energy without requiring any mysterious new substance. In these theories, the accelerating expansion is not caused by dark energy pushing space apart, It is caused by gravity itself behaving differently at very low curvatures and accelerations. Mordechai Milgram's modified Newtonian dynamics, or MOND, proposed in 1983, takes a different approach. MOND suggests that Newton's law of gravity, and by extension Einstein's general relativity, need modification at very low accelerations. On the scale of galaxies, MOND has had some success in explaining the flat rotation curves that Vera Rubin observed without invoking dark matter. But MOND has struggled to explain the full range of cosmological observations, particularly the detailed patterns of the cosmic microwave background and the large-scale clustering of galaxies. Most cosmologists consider the lambda CDM model, with its dark matter and dark energy, to be a more complete and successful framework. Still, the possibility of modified gravity remains an active area of research. If gravity is indeed modified on the largest scales, it could change our predictions for how the voids evolve and how quickly the distances between clusters grow. Observations from Euclid, DESI, and future surveys will help constrain these models by comparing the growth of cosmic structure with the predictions of general relativity. Any discrepancy could point toward new physics. Another theoretical approach involves the integrated Sachs-Wolf effect, predicted by Rainer Sachs and Arthur Wolf in 1967. This effect describes how photons from the cosmic microwave background gain or lose energy as they pass through the gravitational potential wells created by large structures like galaxy clusters and the gravitational troughs associated with cosmic voids. When a photon falls into the gravitational well of a cluster, it gains energy, its wavelength shortening slightly as it accelerates toward the center of mass. When it climbs out the other side, it loses energy, its wavelength lengthening as it decelerates. In a matter-dominated universe without dark energy, the gravitational wells are static and unchanging, and these two effects cancel out perfectly. The photon enters and exits with the same energy. No trace of the cluster remains in the photon's wavelength. But in a universe with dark energy, the situation changes. The gravitational wells are not static. Dark energy is stretching them, weakening them, making them shallower, while the photon is traversing them. Because the well changes during the photon's crossing, the cancellation is imperfect. The photon gains slightly more energy falling into the well than it loses climbing out, because the well is shallower on the exit side than it was on the entry side. The photon emerges with a tiny net energy boost, a slight warming. This effect is extremely subtle. The temperature change it produces in the cosmic microwave background is only about 1/1,000,000th of a degree. Detecting it requires sophisticated statistical techniques. Astronomers compare maps of the microwave background from satellites like WMAP and Planck with maps of the galaxy distribution from surveys like the Sloan Digital Sky Survey. They look for correlations. Are the directions on the sky where galaxy clusters are located slightly warmer in the microwave background than average? Are the directions where voids are located slightly cooler? The answer, after careful analysis by multiple independent groups since about 2004, is yes. The correlations exist. They are weak, but statistically significant, and they confirm that dark energy is actively reshaping the gravitational landscape of the universe, weakening the potential wells of clusters and voids, and altering the properties of the space between the largest cosmic structures. The integrated Sachs-Wolf effect has also been used to study the properties of cosmic voids directly. When a photon passes through a large void, it experiences the inverse of the cluster effect. It loses a small amount of energy entering the void, which has a slight gravitational well even though it is underdense. It gains that energy back leaving. But because dark energy causes the void to expand further, and its already shallow well to become even shallower during the transit, the photon loses slightly more energy than it recovers. The net result is a slight cooling. Photons that have passed through large voids arrive at our telescopes slightly colder than photons that traveled through average density regions. This void-induced cooling has been detected in stacked analyses of the cosmic microwave background, where the signals from hundreds or thousands of individual voids are combined to boost the statistical significance. The results provide direct, observational evidence that the voids between galaxy clusters are not static empty spaces. They are dynamic, evolving structures actively expanding and deepening under the influence of dark energy, imprinting their signature on the oldest light in the universe. The fifth and perhaps most speculative approach has asked whether it might be physically possible to send probes or signals across the expanding voids before they become impassable. This is not mainstream physics. It verges on engineering speculation and even science fiction, but it addresses a question that naturally arises from the science. If the voids are closing off, if the connections between galaxy clusters are being severed, is there time to do anything about it? Could a sufficiently advanced civilization extend its reach across the growing emptiness before the last windows close? The answer depends critically on the target and the timeline. For the Virgo cluster, which is relatively nearby at 65 million light-years and is gravitationally associated with our supercluster, the situation is genuinely ambiguous. The local group is falling toward the Virgo cluster at roughly 200 kilometers per second. Whether this infall will bring us into gravitational contact with the Virgo cluster, or whether the expansion will ultimately pull us away, depends on the precise distribution of mass in the region. And our measurements are not yet precise enough to decide. If we do eventually merge with Virgo, the distance problem to that particular cluster solves itself, but Virgo would still become isolated from all other clusters. For more distant clusters, the calculus is stark. A probe traveling at 10% of the speed of light, roughly 30,000 kilometers per second, a speed far beyond any propulsion technology that currently exists or is even theoretically feasible with current physics, would take roughly 650 million years to reach the Virgo cluster. For the Coma cluster, the journey would take well over 3 billion years, and during that travel time, the expansion of space would have added significant distance to the journey. The probe would not simply cross a fixed gap. It would be chasing a receding target across a stretching landscape. Depending on the precise expansion rate and trajectory, the probe might still arrive, but it would arrive at a cluster that is farther away than it was when the probe launched. For clusters near the current cosmic event horizon, the situation is already and irrevocably hopeless. No probe, traveling at any speed less than the speed of light, could reach them. The space between us and those clusters is expanding faster than any subluminal probe could cross it. The window has closed. For those clusters, the light we see tonight is the last communication we will ever receive. And for every year that passes, the window closes on clusters that are slightly closer. The doors are slamming shut, one after another, each one nearer than the last. Could faster-than-light travel solve the problem? Concepts like the Alcubierre warp drive, proposed in 1994, and traversable wormholes are allowed by the mathematics of general relativity. But both require exotic matter with negative energy density, something never observed in the quantities needed and possibly non-existent. Most physicists consider these concepts mathematical curiosities rather than viable engineering pathways. There is no known physics, no proposed technology, and no theoretical framework that could prevent the isolation of galaxy clusters. The conclusion, even at the most speculative end of the analysis, is sobering. The expansion is a feature of spacetime itself, built into the geometry of the universe by the presence of dark energy. You cannot build a bridge across expanding space because the bridge itself would be embedded in that space and would be stretched along with it. You cannot outrun the expansion because it is not a speed to be outrun. It is a property of the medium through which you travel. Freeman Dyson, the visionary physicist and mathematician, speculated in a landmark 1979 paper about the long-term survival of intelligent civilizations in an expanding universe. He considered how a civilization might manage its energy resources over trillions of years, gradually reducing its temperature and slowing its cognitive processes to stretch its existence across ever longer timespans. Dyson's analysis was optimistic. He concluded that in a decelerating universe, a sufficiently clever civilization could survive indefinitely, processing an infinite number of thoughts across infinite time. But Dyson's analysis assumed a decelerating expansion. The discovery of accelerating expansion in 1998 fundamentally changed the calculus. In an accelerating universe, the energy available to any isolated cluster eventually runs out. Stars die, black holes evaporate. the cosmic microwave background fades below usable temperatures. There is no external source of energy to draw upon because all external sources have been carried beyond the horizon. The civilization is trapped in a finite pool of energy, embedded in a space that is cooling toward absolute zero. Even Dyson's optimistic strategies cannot survive indefinitely in such a universe. The physicist and cosmologist Fred Adams and the astrophysicist Gregory Laughlin explored the long-term future of the universe in their 1997 book, written before the discovery of accelerating expansion but prescient in many ways. They divided the future of the cosmos into eras: the stelliferous era, when stars shine; the degenerate era, when only stellar remnants remain; the black hole era, when only black holes persist; and the dark era, when even black holes have evaporated. Each era lasts far longer than the one before it. The stelliferous era will last roughly 100 trillion years. The degenerate era extends to about 10 to the 39th power years. The black hole era extends to about 10 to the 100th power years. And the dark era stretches beyond comprehension, potentially forever. The numbers here deserve emphasis: 10 to the 100th power years. That is a 1 followed by 100 zeros. It is a number so large that it dwarfs every other timescale we have discussed. The current age of the universe, 13.8 billion years, is less than 10 to the 11th power years. The time until the last star burns out, roughly 10 to the 14th power years, is enormous by human standards but tiny compared to the black hole era. And the dark era, when even the black holes have evaporated into faint radiation, stretches beyond the black hole era into timescales that mathematical notation can barely capture. Throughout all of these eras, the distances between galaxy clusters will continue to grow. By the time the stelliferous era ends and the last star flickers out, every other cluster will have long since vanished beyond the horizon. By the time the degenerate era begins, the concept of galaxy clusters as distinct entities will have been replaced by isolated collections of cooling stellar remnants, white dwarfs and neutron stars slowly radiating their residual heat into an ever emptier, ever colder universe. By the black hole era, even those remnants will have been consumed by or merged into the supermassive black holes that lurk at the centers of galaxies. And by the dark era, even those black holes will have evaporated through Hawking radiation, leaving nothing but a thin sea of photons and subatomic particles spread infinitely thin across an infinitely large space, at a temperature asymptotically approaching absolute zero. The isolation of clusters is not just a feature of the current era, it is a permanent, irreversible change in the structure of the cosmos. Once a cluster is cut off, it is cut off forever. There is no reversal, there is no recovery, the expansion has no reverse gear. There is one more approach worth discussing, though it touches on the foundations of cosmology itself. Some physicists have asked whether the observed flatness of the universe might tell us something about the distances between galaxy clusters and their ultimate fate. General relativity tells us that the presence of matter and energy curves space-time. On the largest scales, the curvature of the universe determines its global geometry. If the total energy density exceeds the critical density, the universe is positively curved, like the surface of a sphere, and is finite. If it is below the critical density, the universe is negatively curved, like a saddle, and is infinite. And if the density is exactly at the critical value, the universe is flat, like a sheet of paper, and is also infinite. Measurements from the Planck satellite have shown that the universe is flat to within about 0.5%. The total energy density, including dark energy, dark matter, and ordinary matter, matches the critical density with extraordinary precision. This flatness has profound implications. In a flat universe with a positive cosmological constant, the expansion continues forever. There is no recollapse. There is no big crunch. The universe stretches into an eternal future of accelerating expansion, cooling and darkening. The distances between galaxy clusters will grow without limit, and no physical process will ever reverse them. Some cosmologists have noted that this flatness is itself mysterious and requires explanation. Why should the density be so close to the critical value? The theory of cosmic inflation provides an answer. During the rapid expansion of inflation, any initial curvature would have been stretched out, driven toward flatness, just as the surface of a balloon becomes flatter as you inflate it. The flatness we observe is a consequence of inflation, which means it is a consequence of the same quantum processes that seeded the density fluctuations that became the voids and clusters. The geometry of the universe, its flatness, is intimately connected to the formation and separation of galaxy clusters. Everything traces back to those first moments. Each of these 5 approaches — measurement, simulation, theoretical analysis, observational testing, and speculative engineering — converges on the same conclusion. The distances between galaxy clusters are real, they are growing, and there is no known way to stop them from continuing to grow. The voids will expand, the clusters will separate. The cosmic web will dissolve into threads, then wisps, then nothing. And the universe, in the fullness of time, will become a collection of isolated islands, each surrounded by an infinity of empty, expanding space, each unaware that the others exist. And this is where the answer becomes deeply unsettling, because the question is no longer whether the clusters will be isolated. That is certain as any prediction in physics can be. The question is what the isolation means, what it means for the nature of the universe as a knowable, comprehensible system, what it means for the possibility of knowledge itself, what it means for the fate of any minds that exist within those clusters, watching the sky go dark, watching the horizons close in, watching the last evidence of a larger cosmos disappear into the expanding void, and what it means for us, here and now, in the brief and privileged era when we can still see the truth. The deeper truth about the distance between galaxy clusters is not a matter of measurement or mathematics. It is not about kilometers or megaparsecs or recession velocities. Those are the language in which the truth is expressed, but the truth itself is something more fundamental. It is a statement about the nature of existence, about what the universe is becoming, about what it means for a cosmos to slowly dismantle the structures it spent billions of years building. The voids between galaxy clusters are not merely empty spaces, they are the future of the universe made visible. They are what everything will eventually become. The clusters, the filaments, the walls, the web itself, all of it is temporary. The voids are permanent, and they are growing. Slowly, relentlessly, inexorably, the voids are swallowing the structures of the cosmos, stretching the connections between clusters, thinning the filaments, deepening the silences. The universe is not building toward some grand climax. It has already passed its structural peak. From here, the arc bends toward dissolution. In the standard cosmological model, the ultimate fate of the universe is known as the heat death. This is not a death by fire. It is a death by equilibrium. The heat death is a state of maximum entropy, the thermodynamic quantity that describes the degree of disorder in a system. In a universe that continues to expand and cool, all energy will eventually be dispersed so thinly and uniformly that no work can be done, no structures can be maintained, no gradients can power any process. Stars will burn out, black holes will evaporate, atoms may decay, if the proton is unstable, as some grand unified theories predict, and the universe will settle into a state of perfect, cold, dark uniformity, where nothing happens, nothing changes, and nothing can ever happen or change again. This is not science fiction. This is the prediction of well-established thermodynamics and statistical mechanics, applied to the best measurements we have of the universe's contents and expansion rate. The heat death is not a speculative scenario debated only on the fringes of physics. It is the consensus view of cosmologists, supported by the lambda CDM model, the cosmic microwave background data, the supernova measurements, and the observed accelerating expansion. It is what happens when you take the laws of physics and project them forward across the vast timescales that the universe has ahead of it. The heat death is not a single moment. It is a gradual, inexorable process that unfolds across time spans so long that the current age of the universe is less than a rounding error. The last stars will burn out in roughly 100 trillion years. That is about 7,000 times the current age of the universe. After the stars die, the universe enters the degenerate era, when the only remaining objects are the cooling remnants of stars, white dwarfs, neutron stars, and brown dwarfs, slowly radiating away their residual heat into an ever colder space. This era lasts for timescales measured in powers of 10 so large that writing them out becomes an exercise in futility. The last black holes will evaporate through Hawking radiation in approximately 10 to the 100th power years. That is a number with 100 zeros after it. And then the dark era begins, a timeless, featureless expanse where nothing of consequence occurs, stretching forward without limit into a future indistinguishable from eternity. Let that sink in. The universe as we know it, with its blazing stars and spiraling galaxies and blue oceans and living forests, is a brief flash in cosmic time, a fleeting sparkle of complexity between the blinding simplicity of the Big Bang and the dead simplicity of the heat death. We live in the bright interlude, the brief epoch when matter is organized enough to form structures, when energy gradients are steep enough to power chemistry and biology, when the temperature differences between stars and the void of space are large enough to sustain the intricate processes that produce and maintain life. This interlude will end, not because of any catastrophe, not because of any disaster, because of the simple, patient, unwinding of thermodynamic processes across cosmic time, and the distances between galaxy clusters are among the first visible signs of that unwinding. They are the leading edge of the dissolution, the place where the expansion is most advanced, the region where the future has already begun. The cosmic web, that beautiful and intricate network of filaments and nodes that connects the galaxy clusters, is a temporary structure. It exists because matter has had enough time to flow along gravitational gradients and concentrate into filaments and clusters, but dark energy has not yet had enough time to tear it apart completely. We live in the brief window between assembly and dissolution, a window that opened roughly 5 billion years ago, when dark energy first became the dominant component of the universe's energy budget, and that will close over the next hundreds of billions of years as the web unravels. Before dark energy took over, the universe was in its constructive phase. Matter was dominant. Gravity was slowing the expansion. The cosmic web was growing denser and more complex with every passing billion years. Clusters were forming at the intersections of filaments, accreting matter from their surroundings, merging with other clusters, growing larger and more massive. The voids were growing too, but slowly, their expansion limited by the decelerating effect of matter's gravity. It was an era of construction, of growth, of increasing complexity. About 5 billion years ago, that era ended. The density of matter, which decreases as the universe expands, dropped below the density of dark energy, which remains constant. Dark energy became the dominant force. The expansion shifted from deceleration to acceleration, and the cosmic web, which had been building for nearly 9 billion years, began its long, slow unwinding. We are now roughly 5 billion years into this new era. The effects are already measurable. X-ray observations of galaxy clusters, made with space telescopes like Chandra and XMM Newton, show that the rate of cluster formation has slowed dramatically. The most massive clusters that will ever exist have already formed. Few new massive clusters will assemble in the future, because the filaments that fed them with gas and dark matter are thinning, and the voids that separate them are expanding. The Sunyaev-Zeldovich surveys, conducted with ground-based instruments like the South Pole Telescope and the Atacama Cosmology Telescope in the high desert of Chile, have confirmed this picture. The population of massive clusters has plateaued. The assembly line is winding down. Let that sink in. The era of cosmic construction is ending. The universe is transitioning from a period of building, of gathering, of concentrating, to a period of dissolution, of dispersal, of thinning. The clusters that exist today are the inheritance of a more active past. They will persist for a very long time, slowly evolving internally as their galaxies merge and their gas cools. But they will not grow significantly larger. They will not gain new members from outside. The voids around them will grow, cutting them off from the raw materials they once drew upon. This transition is not a slow fade in the distant future. It is a process happening now, measurable now, confirmed by multiple independent observations from multiple independent instruments. The universe is becoming lonelier, and the growing distances between galaxy clusters are the proof. There is a thought experiment that makes the implications vivid. Imagine you are an astronomer living inside a galaxy cluster 200 billion years from now. That is roughly 15 times the current age of the universe. A long time by any standard, but well within the stelliferous era, the age when stars still shine. What would you see? You would look up at the sky from whatever planet or habitat you called home, and you would see your own cluster. Perhaps a few hundred galaxies, many of them long since merged into larger, more amorphous structures. You would see old red stars, because the most massive, hottest, bluest stars would have burned out billions of years ago. You might still see some dim, long-lived red dwarfs, stars so feeble and efficient that they can burn for trillions of years, sipping their hydrogen fuel with a miserliness that the sun could never match. But beyond your cluster, you would see nothing. Not a single galaxy, not a single cluster, not a single point of light that does not belong to your own gravitational family. The sky, beyond the familiar stars of your own merged supergalaxy, would be absolutely black. Not the textured black of our current night sky, where even the darkest patches reveal galaxies when photographed with long exposures. True black. The absolute absence of any photon from any external source. The cosmic microwave background, which today fills the sky with a faint but detectable glow at a temperature of about 2.725 Kelvin, would have been redshifted to wavelengths so long that no instrument could detect them. Currently, the peak wavelength of the microwave background is about 1.9 millimeters. In 200 billion years, the expansion would have stretched that wavelength by a factor of millions, pushing it to wavelengths of kilometers or more. A single oscillation of such a wave would take microseconds to complete, and the energy per photon would be so unimaginably low that no physical detector, no matter how sensitive, could register it. The background would have effectively ceased to exist as a measurable phenomenon. The expansion of space would have carried every other cluster beyond the cosmic event horizon. Their light would have been redshifted to infinite wavelength. Not merely very long wavelength. Infinite. This is a mathematical consequence of the exponential expansion driven by a cosmological constant. In the limit, the redshift of a galaxy approaches infinity as its light approaches the event horizon. The frequency drops to zero, the energy drops to zero. The photon, in a practical sense, is annihilated by the expansion, not absorbed, not scattered, not blocked, simply stretched out of existence. You would have no way to know that other clusters exist, no way to know that the universe was ever denser, hotter, or more compact than it is in your time. No way to discover the Big Bang, because the evidence for it, the cosmic microwave background, the primordial abundances of light elements, the observed expansion of galaxies, would all be gone or uninterpretable. No way to detect dark energy, because detecting dark energy requires observing the recession of distant objects, and there would be no distant objects to observe. Your physics would be excellent, your mathematics would be precise, your observations would be meticulous, and your picture of the universe would be profoundly wrong. There is a chilling parallel here. For most of human history, we too had a profoundly wrong picture of the universe. For thousands of years, we believed the cosmos consisted of the Earth at the center, surrounded by crystal spheres carrying the sun, moon, planets, and stars. We believed this not because we were foolish, but because it was consistent with our observations. The sun appeared to rise and set. The stars appeared fixed on a distant sphere. Without better instruments and better theories, the geocentric model was reasonable. The future astronomers in their isolated cluster will face the same predicament, but with a crucial difference. Our wrong picture of the universe was a product of limited technology. Better telescopes and better physics corrected it. Their wrong picture will be a product of limited data. No telescope, no matter how powerful, will correct it, because the data needed for correction has been erased from the observable universe. Their ignorance will be permanent, not because they lack intelligence or curiosity, but because the cosmos itself has hidden the truth. The Krauss and Scherer paper from 2007 described this scenario in meticulous detail. They titled it, The Return of a Static Universe and the End of Cosmology. The title is deliberately provocative. They showed that future observers would, by necessity, develop a cosmology that described a static, unchanging universe consisting of a single cluster of galaxies in an infinite empty void. They would have no observational evidence for expansion, for acceleration, for the Big Bang, or for the cosmic microwave background. Their cosmology would be internally consistent, mathematically rigorous, and completely wrong. Krauss and Scherer went further. They considered whether any traces of our cosmological knowledge might survive into the far future. Could records, archives, or data persist for hundreds of billions of years? The answer is almost certainly no. No physical storage medium can survive the timescales involved. Even the primordial helium abundance, a relic of Big Bang nucleosynthesis that might seem like a lingering clue, would be uninterpretable without the framework of an expanding universe to make sense of it. Future observers would notice the anomalous helium fraction but would have no way to connect it to its true origin. The evidence needed for the connection would have been erased. This is perhaps the most unsettling implication of the distance between galaxy clusters. It is not just that the distances are large and growing, it is that the growth actively destroys information. The expansion of the voids is a form of cosmic censorship, hiding the true nature and history of the universe from any observer who arrives too late to see the evidence. It is as though the universe is writing its autobiography in disappearing ink, the words fading even as the pages turn, leaving behind blank sheets that reveal nothing about the story that was once written on them. We are not too late, not yet. We live in the era when the cosmic microwave background is still detectable, when its temperature can be measured to 6 decimal places, when its polarization patterns can be analyzed to reveal the physics of inflation. We live in the era when distant galaxy clusters are still visible, when their redshifts can be measured, when their motions can be tracked, when their X-ray emissions can be studied. We live in the era when the cosmic web can still be mapped, its filaments traced, its voids measured, its structure compared with the predictions of our cosmological models. We have access to information that will eventually be lost, permanently and irrecoverably. We can see the web. We can measure the Hubble parameter imperfectly, with tension and uncertainty, but we can measure it. We can detect dark energy through the recession of distant supernovae. We can reconstruct the history of the universe from the first fraction of a second to the present day, a reconstruction that future observers will be unable to perform because the raw data will have been carried beyond the horizon. The astronomer Abraham Loeb of Harvard has emphasized this point repeatedly in his work. He has argued that we are living not just in a technologically privileged era, but in a cosmologically privileged era. The universe is currently at a stage where its structure is visible, its history is readable, and its future can be predicted. This stage will not last. The data that enables modern cosmology is perishable. The observations that led to the discovery of the expanding universe, the cosmic microwave background, and dark energy were possible because those phenomena are currently detectable. In the far future, they will not be. The cosmic clues will have been swept away by the expansion. But this window of knowledge is finite. It has a beginning, roughly corresponding to the epoch when the first intelligent observers developed the technology to study the cosmos. And it will have an end, the epoch when the last cosmologically informative signals fade below the threshold of detectability. Between those two moments, the universe is an open book. After the window closes, the book is shut, and no key will ever reopen it. The distances between galaxy clusters mark the borders of this window. As those distances grow, the horizons shrink. The amount of accessible information decreases. The record of the universe's history is being edited, not by any intelligence, but by the blind mechanics of expansion, erasing entries one by one until the ledger is nearly empty. There is one more dimension to this deeper truth that deserves careful attention. The distances between galaxy clusters are not growing uniformly in the sense that all clusters lose contact simultaneously. They are growing in a nested hierarchy of isolation. The most distant superclusters will be cut off first, their light fading beyond detection within the next few tens of billions of years. Then the nearer superclusters will follow. Then individual clusters within our own supercluster will begin to separate beyond recoverability. Then possibly even the components of our local gravitational neighborhood, depending on the precise balance of gravity and expansion in our region. This hierarchical isolation has a haunting quality to it. It means that the universe does not go dark all at once. It goes dark in layers. First the most distant lights wink out, then the nearer ones. Then the ones you thought were permanent. Each loss brings the darkness a little closer, the visible universe a little smaller, the sense of isolation a little sharper, and each loss is final. Once a cluster crosses the horizon, it does not return. The process moves in only one direction, and it never reverses. There is a word in Japanese, mono no aware, that describes a gentle sadness at the passing of things, a bittersweet awareness of impermanence. The distances between galaxy clusters and their relentless growth evoke something like that awareness at a cosmic scale. The universe in its current form is beautiful. The cosmic web is intricate. The clusters are magnificent, and all of it is passing, not because of any flaw or failure, because expansion is the nature of the cosmos, because dark energy is embedded in the fabric of space, because the geometry of the universe allows no other outcome. The process is like watching an archipelago slowly submerge as sea levels rise. First, the most distant islands vanish below the waves, their mountain peaks disappearing one by one beneath the advancing water. Then the islands nearer to your own coastline begin to go under, their forests and beaches swallowed by the rising sea. Then the beaches of your own island start to shrink, the waterline creeping inward, covering the roads, the villages, the fields. Eventually, you are standing on the last hilltop, watching the water close in around you, surrounded by an ocean that stretches to every horizon, covering everything that was once visible, everything that was once known. But there is a crucial difference between the rising sea and the expanding void. A rising sea is reversible. It can recede. The islands can re-emerge. The water can drain. The expansion of cosmic voids, driven by a cosmological constant, is not reversible. It is a one-way process. The islands of matter that disappear below the cosmic horizon do not come back. They are gone. The sea of expanding space does not recede. It grows deeper, wider, and emptier with every passing moment. This is not science fiction. This is the trajectory of the universe as described by our best physical theories, confirmed and refined by decades of observations from the most powerful and precise instruments that human beings have ever constructed. The Planck satellite, the Hubble Space Telescope, the James Webb Space Telescope, launched in December of 2021, and now the most powerful observatory ever placed in space, capable of seeing galaxies that formed when the universe was less than 300 million years old, the Sloan Digital Sky Survey, DESI, Chandra, XMM Newton, the South Pole Telescope, the Atacama Cosmology Telescope. Every one of these instruments, every one of these missions, every one of these datasets points to the same conclusion. The universe is expanding. The expansion is accelerating. The distances between clusters are growing, and the growth will continue, unchecked, into the indefinite future. Every image captured by the James Webb Space Telescope is, in a sense, a document of a vanishing universe. The distant galaxies in its deep field images are objects whose light has traveled for billions of years to reach its mirrors. Many of those galaxies are already beyond the cosmic event horizon. The light we see from them is ancient light, emitted when they were closer, when the expansion had not yet carried them beyond reach. New light from those galaxies will never arrive. The images in our archives are the last record of their existence that any observer in our corner of the universe will ever possess. Every spectrum measured by DESI, every gravitational lens detected by Euclid, every supernova catalogued by the Vera Rubin Observatory, which is expected to begin its 10-year survey in the mid-2020s. These are not just scientific measurements. They are acts of cosmic documentation. They record the state of the universe during the brief window when the universe is willing to reveal itself. Future instruments may be more powerful, more sensitive, more precise, but they will have less to see. The data that matters most, the data that reveals the true size, age, structure, and fate of the cosmos, is fading, and it will not return. The philosophical weight of this realization is considerable. We are accustomed to thinking of the universe as a place of grandeur and endless possibility. A cosmos filled with hundreds of billions of galaxies stretching in every direction, each one a whirlpool of stars and worlds, each one a potential home for life and consciousness. And that picture is accurate. Right now, in this moment, the universe is vast and rich and full, but the universe we see today is a temporary arrangement, a snapshot of a cosmos in transition. The grandeur is real, but it is passing. The light from distant clusters is already dimming, already stretching, already slipping toward the red end of the spectrum. The connections between cosmic structures are fraying, the filaments are thinning. The web is coming apart, not with violence, not with drama, not with the crash of colliding worlds or the flash of exploding stars, with the quiet, patient, relentless work of expanding space, with the gentle, continuous, unstoppable stretching of the void. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. We exist in a moment when the universe is structured enough to be interesting and transparent enough to be understood. Before this moment, in the hot, dense plasma of the early universe, there were no structures to study and no observers to study them. After this moment, in the cold, empty, isolated future, there will be structures, but no way to see beyond them, no way to understand the larger context in which they exist. We occupy the narrow window between too early and too late. There is something in that realization that deserves to be held carefully, without sentimentality but also without dismissal. The fact that we can see the cosmic web, that we can measure the expansion, that we can detect the microwave background, that we can count the galaxy clusters and trace their distribution across billions of light years, this is not a given. It is a consequence of our position in cosmic history. It is a privilege that comes with an expiration date. And in the end, after enough time has passed, each galaxy cluster will be an island, not an island in an archipelago, surrounded by other islands that can be reached by boat or seen from the shore. An island in an empty sea, utterly alone, with no other land in any direction, no horizon but the featureless circle of water meeting sky, no other voice to hear across the water, no sail on any horizon. A single cluster of aging stars in a universe that has forgotten everything else, a speck of organized matter in an infinity of darkness, a remnant of a former richness that no future observer will have reason to suspect ever existed. That is the deeper truth of the growing distance between galaxy clusters. The distance is not just a measurement. It is not just a fact to be catalogued. It is a prophecy. A quiet, patient, implacable prophecy written into the geometry of spacetime itself, spoken by the expansion of the void, confirmed by every observation of the accelerating cosmos, and understood, affirmed, in this brief era, by minds that are themselves temporary arrangements of atoms in a universe that will eventually forget they existed. The universe is dissolving. The connections are being severed. The silence between the clusters is growing wider and deeper with every passing moment, and there is nothing, in any physics we know or can imagine, that can stop it. What does this mean for humanity? What does it mean that the universe is built on a foundation of separation that grows wider every moment? What does it mean that the spaces between the great structures of the cosmos are expanding, accelerating, and will eventually erase all evidence that those structures were ever connected to each other? On one level, it means nothing to our daily lives. The expansion of space between galaxy clusters happens on scales so vast and over time periods so long that no human being, no human civilization, will ever experience its effects directly. The sun will exhaust its hydrogen fuel and expand into a red giant in about 5 billion years, long before the isolation of galaxy clusters becomes personally relevant to anything alive on Earth. The Milky Way will merge with Andromeda in roughly 4.5 billion years, producing a combined galaxy that will be our home, if any descendant of ours still exists, for far longer than the current age of the universe. The challenges facing humanity, climate change, resource depletion, the survival of civilizations across centuries and millennia, are all profoundly local problems, operating on profoundly local timescales. The cosmic voids are not going to affect your commute. But on another level, the growing distance between galaxy clusters means everything, because it tells us something fundamental about the nature of the cosmos we inhabit. It tells us that the universe is not designed for permanence. It tells us that complexity, structure, and connection are temporary states, brief islands of order in an ocean of entropy that grows wider and deeper with every passing moment. It tells us that the forces that built the universe, gravity, nuclear physics, and the cooling of an initially hot plasma, are the same forces that will eventually be overwhelmed by the relentless expansion of space. The universe used these forces to build itself, and expansion will, given enough time, dismantle what was built. There is a kind of cosmic tragedy in this. The universe labored for billions of years to produce the structures we see today. From the hot, dense, undifferentiated plasma of the early cosmos, matter slowly cooled and condensed, atoms formed, clouds of gas collected under gravity, stars ignited, galaxies assembled. Clusters gathered at the intersections of the cosmic web. The process was slow, improbable, and magnificent. At every step, the odds favored disorder. The universe had to fight its own tendency toward randomness to produce the structured, beautiful cosmos we observe. And yet, somehow, here we are. Stars shine. Galaxies spiral in luminous pinwheels of light. Galaxy clusters pulse with hot gas and dark matter halos. And on at least one small rocky planet, orbiting an unremarkable yellow dwarf star in an unremarkable spiral galaxy, life emerged, evolved, and eventually developed the capacity to understand the cosmos that produced it. But the same expansion that allowed these structures to form, by giving matter space to cool and condense, is now working to tear those structures apart. The expansion was essential for creation. It gave the hot plasma room to cool. It allowed density fluctuations to grow into clusters. It was the necessary condition for the complexity we observe. And now that same expansion, amplified by dark energy, is the instrument of dissolution. The universe used expansion to build itself, and expansion will eventually destroy what it built. There is a deep, inescapable irony in this. The tool of creation is also the tool of destruction. The architect is also the demolisher. This is not a new idea in human thought. Many philosophical and religious traditions have grappled with the tension between creation and destruction, between order and chaos, between the fleeting nature of existence and the longing for permanence. The ancient Greek philosophers debated whether the cosmos was eternal or subject to change and decay. The Hindu concept of the cosmic cycle describes a universe that is endlessly created and destroyed. The Buddhist teaching of impermanence, anicca, holds that all compounded things are transient, arising and passing away in an endless flow. The Stoic philosophers saw the cosmos as a living fire, perpetually consuming and regenerating itself. Modern cosmology now gives these ancient intuitions a precise mathematical expression. The universe is not eternal in the way the ancients debated. It changes, it evolves. It expands, cools, structures, and then slowly decomposes under the influence of dark energy and the second law of thermodynamics. The distances between galaxy clusters, growing every moment, are the clearest physical manifestation of this impermanence. They are the ticking of a cosmic clock that counts down to a future of isolation and stillness. They are the proof, written in the geometry of spacetime, that nothing lasts. There is a particular poignancy in the fact that we have discovered this truth at the very moment when it matters most. A few centuries ago, we did not know that galaxies existed. A century ago, we did not know the universe was expanding. A quarter century ago, we did not know the expansion was accelerating. Each discovery has arrived just in time to be discovered before the evidence begins to fade. Had intelligent life arisen 1 trillion years from now instead of now, it would never have known any of this. The cosmic microwave background would have been undetectable. The distant clusters would have been invisible. The expansion would have been unmeasurable. The entire edifice of modern cosmology, from the Big Bang to dark energy, would have been undiscoverable. We arrived at the right time. Whether by chance or by some deeper necessity that we do not yet understand, we are here at the moment when the universe is most knowable, and that moment is passing. Pause on that. Consider what it means to live at the unique point in cosmic history when the universe reveals itself most fully. Before this era, the universe was too hot and opaque for structures to exist or observers to form. After this era, the universe will be too expanded and empty for its history to be readable. We sit at the apex of knowability, the peak of the curve, the summit from which the view is clearest. This raises a question that cosmologists have debated quietly, and sometimes not so quietly, in recent years. Does our position in cosmic time impose a special responsibility? If we are the generation with the most cosmological information available, do we have an obligation to preserve it, to record it in forms that might survive, to create archives of cosmological knowledge that could, in principle, outlast the evidence itself? The practical answer is almost certainly no, at least not in terms of physical records. No storage medium can survive the timescales involved. The longest-lived geological records on Earth persist for billions of years, but even they will be destroyed when the sun expands into a red giant. Digital storage is far more fragile. The Library of Congress, the largest library on Earth, stores its information on media that degrades over decades or centuries without active maintenance. The idea of preserving cosmological knowledge for trillions of years is, with current technology, a fantasy. But the philosophical answer is more nuanced. Perhaps the preservation that matters is not physical but intellectual. Perhaps the act of understanding the universe's fate, the act of comprehending the growing distances between galaxy clusters and what they mean, is itself the preservation. We cannot save the data for future observers who will never have access to it. But we can understand it now, fully and deeply, and in doing so, we can fulfill whatever role consciousness plays in a cosmos that produced it. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. We exist in a moment, a cosmic moment, when the universe is young enough to be interesting and old enough to be comprehensible. We can see the stars because they still shine. We can detect the cosmic microwave background because it has not yet faded beyond all detection. We can map the cosmic web because it still exists. These are not permanent abilities, they are gifts of timing. Gifts that come with the implicit understanding that they will be withdrawn. And there is something in that awareness that should inform how we think about our own era, our own science, our own efforts to understand the cosmos. Every galaxy survey, every cosmic microwave background measurement, every dark energy experiment is not just an exercise in scientific curiosity, it is an act of cosmic documentation. We are recording the state of the universe during its brief, readable era, preserving information that the expansion is in the process of erasing. We are the scribes of a cosmos that is writing its own obituary. The James Webb Space Telescope, peering into the deep past to see the earliest galaxies, is documenting a universe that will eventually become invisible. The DESI survey, mapping the expansion history of the cosmos, is measuring a process that will eventually become unmeasurable. The Planck satellite's maps of the cosmic microwave background are portraits of a signal that will eventually become undetectable. Every one of these observations captures a moment that will not return. The universe will move on, the evidence will fade, but the measurements, if they survive in some form, will be the record of a truth that the cosmos itself has chosen to forget. There is a strange and humbling beauty in this role. We are small, we are brief. We occupy a single planet, orbiting a single star, in a single galaxy, in a single cluster. We have existed for a tiny fraction of the age of the universe. We may exist for only a tiny fraction more, but we can see the cosmos. We can measure its expansion. We can predict its fate. We can understand, at least in broad strokes, what the universe has been, what it is now, and what it will become over the next 100 billion years and beyond. No other entity that we know of has ever done this. No other collection of atoms, anywhere in the observable universe has demonstrated the ability to comprehend the scale and trajectory of the cosmos. We are, as far as we know, the universe's only conscious witness to its own dissolution, and there is something in that role that transcends the distances, the timescales, the entropy, and the inevitable isolation of the galaxy clusters. We are the universe looking at itself and understanding what it sees, and what it sees is vast and temporary and beautiful and passing. The voids between galaxy clusters are enormous. They are growing. They will eventually swallow all evidence of the universe's former connectedness, erasing the record of a richer, more structured past. But for now, for this brief and precious moment in the life of the cosmos, we can see across them. We can measure their extent. We can calculate their growth rate. We can understand what they mean and what they foretell. And in understanding them, we are doing something that the universe itself cannot do without the minds and instruments that it produced. We are remembering. We are bearing witness to a cosmos that is in the slow process of forgetting itself. We are holding, for as long as our species and our records endure, the image of a universe that is in the act of disappearing. That image, that understanding, that act of witness may be the most meaningful thing that any arrangement of atoms has ever accomplished in the entire history of the cosmos. The distances between galaxy clusters will continue to grow. The darkness will continue to deepen. The isolation will continue to spread. But for now, in this moment, we know, we see, we understand. And that is enough. That has to be enough, because it is all the universe has given us, and it is more than any future observer will ever receive. The distance between galaxy clusters is measured in millions and billions of light years. But the true measure of that distance is not in light years or megaparsecs, or any other unit that astronomers inscribe in their databases. The true measure is time. It is the slow, silent, relentless stretching of space that separates one island of matter from another, pushing them apart with a force that cannot be resisted, a force that cannot be reasoned with, a force that has no purpose, no intention, and no off switch, just expansion, just the geometry of a cosmos that will not stop growing. We began tonight with a single observation. The spaces between galaxy clusters are enormous, darker, emptier, and more silent than any terrestrial analogy can capture. And they are growing, driven by accelerating expansion, fueled by the mysterious dark energy that fills every cubic centimeter of the cosmos. We explored how those spaces are measured, tracing the cosmic distance ladder from parallax to Cepheids to supernovae. We examined how they formed, seeded by quantum fluctuations in the first fraction of a second after the Big Bang, sculpted by gravity across billions of years, and stretched by dark energy. We followed the history of cosmic expansion from Lemaitre and Hubble to Perlmutter, Schmidt, and Rius. We confronted the Hubble tension, a crack in the foundation of modern cosmology. We examined dark energy, the mysterious force driving the acceleration. We looked at the cosmic web and watched it begin to unravel. We ran the simulations forward and saw the filaments thin, the voids deepen, the clusters drift apart into isolation. We considered the future observers, trapped in their lone clusters, surrounded by impenetrable darkness, unable to know that the universe was ever larger, richer, or more connected than the small patch they can see. And we arrived at a truth that is both terrifying and, in its way, strangely beautiful. The universe is a place of temporary connections. The galaxies we photograph are connected now, bound by gravity, linked by filaments of dark matter and gas, visible to each other across the voids. But those connections are weakening, the filaments are thinning, the voids are deepening. And one by one, the lights in the cosmic sky will go out, not because they stop shining, but because the space between us and them will stretch the light beyond all possibility of detection. The photons will still be travelling, but they will be stretched to wavelengths longer than galaxies, longer than clusters, longer than meaning. The Milky Way will merge with Andromeda. Our local group will consolidate into a single large elliptical galaxy. And that galaxy, or whatever it becomes across the eons, will drift in an ever-expanding void, the last structure in an empty observable universe. No cosmic web, no distant clusters. No cosmic microwave background, just one island of aging stars in an infinite sea of darkness, a single ember in a fireplace that has gone cold. This is the future that the distance between galaxy clusters foretells, not a violent end, not a dramatic collapse, not the bang of a big crunch or the snap of a big rip, a quiet fading, a slow, gentle, implacable retreat into isolation. The universe will not end with a spectacular event that compresses all of existence into a single point. It will end with a distance too great for any signal to cross, too vast for any light to bridge, too wide for any knowledge to span. The end of the universe, if it can be called an end, is not a wall, it is a horizon that retreats forever, carrying everything beyond it into unreachability. There is something almost meditative about this fate. It lacks the drama that our storytelling instincts crave. We want our endings to be decisive, climactic, definitive. A big crunch would have been dramatic. A big rip would have been violent. But the actual fate of the universe, as best we can determine, is neither dramatic nor violent. It is patient. It is gradual. It is the cosmic equivalent of a long, slow exhalation, a breath released so slowly that you barely notice the air leaving, until the lungs are empty and the silence settles in. And yet, here we are, in this narrow, fragile, luminous window of cosmic time. We can see the Virgo cluster, 65 million light-years away, glowing with the light of thousands of galaxies. We can detect the cosmic microwave background, a whisper from the universe's first moments, still audible after 13.8 billion years of travel, filling the entire sky with its faint, ancient warmth. We can measure the Hubble parameter, imperfectly, incompletely, with a tension that tells us our understanding is not yet finished, that there are surprises still waiting in the data. We can run computer simulations of the cosmic web and compare their predictions with the observed distribution of millions of galaxies, and find that our models work, that our physics is right, that we understand the architecture of the cosmos even as it comes apart. We can look out across the voids, across the hundreds of millions of light-years of expanding nothing, and see the faint glow of distant superclusters. Structures so remote that their light has been travelling since before the Earth existed. Structures that are already being pulled away from us by the expansion, their light stretching and dimming with every passing year. Structures that our grandchildren's grandchildren, 1,000 generations hence, will still be able to see, but dimmer, fainter, redder. Until eventually, in the far future, they will fade below the threshold of any instrument, and the sky will hold one fewer light. We are the witnesses. We are the measurers. We are the ones who noticed the distance between the galaxy clusters and asked what it meant. We are the ones who built the telescopes, designed the surveys, wrote the equations, ran the simulations, and arrived at an answer that is at once devastating and beautiful. The universe is vast. The universe is temporary. The universe is dissolving. And what it means is this: the universe is not eternal in the way anyone once imagined. It changes, it grows, it cools, it fades. The structures we see today, the clusters and filaments and walls and sheets of galaxies that make up the cosmic web, are the remnants of a denser, hotter, more connected past. And they are the precursors of a colder, darker, more isolated future. We stand between these two states, between the fire of the Big Bang and the ice of the heat death, between the dense, opaque past and the empty, transparent future, and we are the ones who understand the transition. We are the ones who can see both directions. The distance between galaxy clusters is the measure of that transition. It is the ruler by which the cosmos marks its own progression, from birth to dissolution. It is the measure of how far the universe has come from its fiery beginning, and it is the measure of how far it must go before the last star burns out, the last black hole evaporates into a whisper of radiation, and the last photon redshifts into a wavelength longer than the observable universe itself, carrying its tiny quantum of energy into a cosmos that has no use for it. There is a term in cosmology for the era we inhabit. It is called the stelliferous era, the age of stars. It began when the first stars ignited, roughly 100 to 200 million years after the Big Bang, and it will end when the last stars exhaust their fuel in roughly 100 trillion years. We are near the beginning of this era. The universe is young, the stars are still plentiful, the galaxies are still bright. The cosmic web still connects the great structures of the cosmos, however thinly, however tenuously. But the stelliferous era is just one chapter in a much longer, much darker story. A chapter that is brief and luminous, and filled with structure and complexity and, on at least one planet, with life and thought and wonder. And after this chapter ends, the story continues for timescales so long that the stelliferous era shrinks to a footnote, a flash, a spark in the darkness. And throughout all of those future eras, across all of those inconceivable spans of time, the distances between galaxy clusters will continue to grow. The voids will expand, the darkness will deepen, the silence will thicken, until nothing remains but the void itself, stretching in every direction, without limit, without change, without witness. And so we return to where we began. Right now, as you listen to these words, the space between galaxy clusters is growing. Not slowly, not gently, silently, persistently, irrevocably. The voids are deepening. The clusters are drifting apart. The light between them is stretching, thinning, fading. The universe is vast beyond comprehension. It is beautiful beyond description, and it is temporary beyond measure. The distances between galaxy clusters are the proof. They are the signature of a cosmos that is, moment by moment, photon by photon, slipping away from itself. And we, on our small planet, orbiting our ordinary star, within our unremarkable galaxy, bound to our modest cluster, are the ones who noticed. We looked into the darkness between the galaxy clusters, and we saw the future written there. We measured the growing silence and understood its meaning. We are temporary, and we know it. The universe is temporary, and we know that too. That knowledge is our gift, and perhaps, in some small way, our purpose. We live in the age when the cosmos still speaks to us, still sends its light across the voids, still reveals its history in the faint glow of distant clusters and the whisper of the microwave background. That age will pass, the speaking will stop, the light will fade, the silence will become absolute. But not yet, not tonight. Tonight, the light is still arriving. End of script. Total word count, 25,484.